Hello there, and welcome to the Cosmographer. The faintest constellation in the sky, the one whose brightest star is barely visible from a dark garden, contains an entire galaxy inside its borders, and the man who drew it put the galaxy there on purpose, as a joke about the weather. That is only number 10 on this list. Further down is the only constellation ever cut in half by a committee, which happens to hold the most reproduced photograph in the history of astronomy. Below that is a little fox, invented in 1687 to fill an empty gap, where a 24-year-old student found the first pulsar on a roll of chart paper. And further down still is a constellation named after a carpenter's square, hiding the thing our entire galaxy is falling toward at 630 kilometers per second. The constellation at the top of this list is first for a reason that has nothing to do with what is inside it. 10 constellations, counted down from 10 to 1, ranked by the gap between the figure drawn on the chart and the thing standing behind it. Get comfortable and settle in. If a long, slow walk through the sky's filing system sounds like a good night to you, a quiet like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the constellations will not look like patterns anymore. They will look like windows. Let's begin at number 10. Number 10, Mensa, the table that holds another galaxy. There are 88 constellations in the sky, and not one of them is a thing. A constellation is a direction with a fence around it. The fences were drawn by a committee. Between 1922 and 1930, the International Astronomical Union asked a Belgian astronomer named Eugene Delporte to settle the boundaries once and for all, and he did it by ruling straight lines along the coordinates of the sky as they stood in 1875. Every square degree of the sky now belongs to exactly one constellation, the way every acre of land belongs to exactly one county. What that means is easy to state and surprisingly hard to feel. The stars inside any one constellation have nothing to do with each other. They sit at wildly different distances, moving in different directions at different speeds, and they were born in different places at different times. The pattern exists only from here. Move a few hundred light years in any direction, and every figure in the sky comes apart. So the contents of a constellation are, in the strictest sense, an accident. Whatever lies inside those fences is there because of where we happen to be standing. And that is what makes this list worth 3 hours, because the accidents are not distributed evenly. Some of these squares of sky are conspicuously ordinary. They are faint. No ancient culture named them. Several of them were improvised in the 1750s by a surveyor who needed somewhere to file the leftover stars. And those same ordinary squares turn out to contain the first pulsar, the first evidence for dark matter, the largest explosion ever measured, and the thing our entire galaxy is falling toward. This is a countdown through 10 of those mismatches. We are ranking them by how wide the gap is between the figure drawn on the chart and the thing sitting behind it. We begin with the faintest constellation in the sky. Mensa is the dimmest of the 88. Its brightest star, Alpha Mensae, shines at magnitude 5.09, which makes it the dimmest Lucida in the entire sky. A Lucida is simply the brightest star of a constellation, the one the eye lands on first, and every other constellation has one that outshines this. Nothing in Mensa is bright enough to be seen reliably from a suburban street. It covers 153 square degrees, which puts it 75th out of 88 by area. It contains no Messier object, no naked eye cluster, and no star with a proper name anyone uses. It is worth pausing on what magnitude actually means, because the number will come up repeatedly tonight. The scale runs backward. Lower numbers are brighter. The brightest star in the night sky sits at about -1.5. The faintest stars a person can see from a genuinely dark sight sit at about 6, and each step of 1 magnitude is a brightness ratio of roughly 2.5 times. Magnitude 5.09 is not invisible. From a dark sight, with no moon and no cloud, and eyes fully adapted, it is there. From anywhere with streetlights, it is not. Mensa is a constellation you can only meet under the right conditions, and even then it does not announce itself. There is also a geographic reason nobody in the classical world named this patch. Mensa sits close to the south celestial pole, at declinations between about 70 and 85 degrees south. From Europe, from the Mediterranean, from anywhere the Greeks or the Babylonians or the Arab astronomers of the medieval period were working, it never rises at all. It is permanently below the horizon. Lacaille had to sail 4,500 nautical miles to see the sky he was mapping, which is the reason this part of the sky has an 18th century name attached to a piece of surveying equipment rather than a myth attached to a hero. It exists because of one man and one mountain. Nicolas Louis de Lacaille was a French astronomer who sailed to the Cape of Good Hope and spent the years 1751 and 1752 mapping the southern sky from a small observatory in what is now Cape Town. He was working with a telescope whose aperture was about ½ an inch across, which is smaller than the lens in a pair of reading glasses. With that instrument, in under 2 years, he fixed the positions of 9,766 stars. His catalogue remained the standard southern reference for generations afterward. The catalogue itself deserves a sentence, because the scale of it is easy to skip past. 9,766 stars, positions measured and reduced in under 2 years by one man working most nights. He also measured the arc of the meridian across southern Africa, determined the lunar parallax, and made the first reasonably accurate measurement of the distance to the moon using simultaneous observations from Berlin. He did all of that on the same trip. Lacaille is not a household name, and the 14 constellations he improvised out of necessity are the least celebrated in the sky, and between them they cover a substantial fraction of everything visible from the southern hemisphere. The southern sky, at that point, was a filing problem. The classical constellations had been drawn by people who lived in the northern hemisphere and had never seen most of it. Lacaille had thousands of stars and nowhere to put them, so he invented 14 new constellations. Almost all of them honor the instruments of the Enlightenment, because that is what he thought the sky should be made of. The air pump, the chemical furnace, the microscope, the telescope, the pendulum clock, the mariner's compass, the sculptor's studio, the painter's easel, the carpenter's square, the level, the octant, the reticle in an eyepiece. It reads like an inventory of a well-equipped workshop, and in a sense, that is exactly what it is. Only one of the 14 honors a place on Earth. He called it Mons Mensae, the Table Mountain, after the flat-topped mountain standing over his observatory. The name was formalized in 1754 and later shortened to Mensa, which means simply the table. It is the only constellation named after a terrestrial geographic feature, and if that were the whole story, it would be a pleasant footnote. It is not the whole story. There is a detail in the design that is easy to miss and hard to forget once you have seen it. Table Mountain is famous for a cloud. When a southeasterly wind pushes moist air up the mountain's face, the moisture condenses at the rim and pours over the flat summit in a smooth white sheet. The people of Cape Town call it the tablecloth. It arrives most afternoons in summer, and it is one of the most recognizable weather phenomena on the African coast. Mikhail watched it from below every day for 2 years while he worked. When he placed his constellation in the sky, he placed it directly beneath the Large Magellanic Cloud. That was deliberate. The Large Magellanic Cloud is a soft, detached patch of light in the far southern sky, visible to the unaided eye from anywhere below the equator, and to a person looking up, it does resemble a piece of cloud that has torn away from the Milky Way. Mikhail set his mountain underneath it so that the galaxy would sit on the table the way the cloth sits on the mountain. It is the only constellation in the sky designed as a landscape with its own weather. And the weather is a galaxy. The southern portion of the Large Magellanic Cloud crosses into Mensa's official borders. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, roughly 160,000 light-years away, about 14,000 light-years across, containing something on the order of 30 billion stars, along with around 60 globular clusters and thousands of smaller ones. It is the fourth closest galaxy to our own, and from the southern hemisphere, it is one of the most obvious things in the night sky. The Large Magellanic Cloud is also not alone. It has a smaller companion, the Small Magellanic Cloud, and the two of them are connected to each other and to our own galaxy by a stream of hydrogen gas hundreds of thousands of light-years long, called the Magellanic Stream. That stream is invisible in ordinary light. It shows only in radio at the 21-centimeter wavelength that neutral hydrogen emits, and it was mapped by radio telescopes decades before anyone could explain it. It is the trail of gas being pulled out of the two smaller galaxies as they move, and it is one of the clearest pieces of evidence that these are not quiet, stable companions, but objects actively being taken apart. Inside the Large Magellanic Cloud's Mensa portion, there are star clusters of every age, from old globulars that formed with the galaxy to open clusters still wrapped in the gas that made them. The Large Magellanic Cloud has a property that makes it extremely useful to astronomers, which is that everything in it sits at essentially the same distance from us. In our own galaxy, comparing two star clusters means first working out how far away each one is, and distance is the hardest measurement in astronomy. In the Large Magellanic Cloud, that problem disappears. If one object looks brighter than another, it is brighter. A great deal of what we know about how stars of different masses live and die was worked out by looking at this galaxy for exactly that reason. The border should be described honestly, because it matters. The Large Magellanic Cloud's most famous features do not fall in Mensa. The Tarantula Nebula, the largest star-forming region known in the local group of galaxies, sits on the Dorado side of the line. So does the site of supernova 1987A, the closest supernova observed in modern times. Mensa holds the galaxy's quieter southern half. What that half contains is still thousands of star clusters, star-forming complexes, and a stellar population that outnumbers everything else in the constellation by a factor no reasonable person would guess from looking at it. Which produces an arithmetic worth sitting with for a moment. Alpha Mensae, the brightest thing in the constellation, is a yellow dwarf about 33 light-years away. It is very nearly a twin of the Sun in mass, temperature and color, and it carries a faint red dwarf companion at an enormous separation. It is close, in stellar terms. It is one of the nearest solar analogues we know of, and it is barely visible. Behind it, in the same square of sky, sits a galaxy 5,000 times further away, containing tens of billions of stars. And the galaxy is easier to see. That is the first correction this list will make, and it is worth stating plainly before we go any further. Emptiness is never a measure of what is there. A faint patch of sky is not a sparse one. It is a patch where the things that happen to be nearby are unimpressive, and where the things that are impressive happen to be a very long way off. The eye reports brightness. Brightness is a combination of how much light something emits and how far away it is, and those two numbers can conspire in any direction they like. There is a second thing filed under this direction, and it arrived much more recently. In August of 1999, the Chandra X-ray Observatory opened its instruments for the first time. First light, as astronomers call it, is a ceremonial moment as much as a technical one. You point the new telescope at something you already understand, so that you can check the instrument against a known answer. The target chosen was a quasar in this far southern region of the sky, catalogued as PKS 0637-752. A quasar is the blazing center of a distant galaxy, powered by matter falling into a supermassive black hole, and this one had been studied in radio for years. It was supposed to be a calibration source. The image that came back showed a jet, a narrow beam of material streaming out of the quasar's core, extending for hundreds of thousands of light years and glowing brightly in X-rays along its entire length. That was not what anyone had predicted. Jets like that were known in radio, but the X-ray brightness along the full length of this one did not fit the models of how such jets radiate. Papers were written about it for years afterward. The first light of a flagship observatory, and the first thing it saw, was something no model had accounted for. It came from the emptiest quarter of the sky. What remains genuinely unsettled here concerns the large Magellanic Cloud itself. Precise measurements of its motion across the sky, first from the Hubble Space Telescope and later from the Gaia astrometry mission, show it moving at roughly 320 kilometers per second relative to the Milky Way. That is faster than a long-settled satellite galaxy should be moving. It is fast enough that a serious body of work now argues the large Magellanic Cloud is on its first pass, a galaxy we have only recently captured rather than one we have always held. Its mass is under revision as well, and the revisions have all been upward. Current estimates put it somewhere between 10 and 25% of the Milky Way's total mass. That is heavy enough to matter. It is heavy enough that the large Magellanic Cloud is measurably pulling our own galaxy off-center, dragging the disk we live in toward it as it passes. The tablecloth, in other words, may be heavy enough to move the table. Lacaille himself did not live to see any of this. He returned from the Cape, spent 4 more years reducing his observations, and died at 49, reportedly worn out by the work. All 14 of his constellations survive in the modern 88, which means no single person in history is responsible for more of the official sky than a man who mapped it with a half-inch telescope from a garden below a mountain. He drew the faintest square in the sky, put a galaxy on top of it as a joke about local weather, and the joke turned out to be the most substantial thing in the constellation by an enormous margin. The emptiest square of sky any human ever drew contains more stars than every constellation we can actually see, all of them together, which tells you that the sky's apparent emptiness has never once been a measure of what is in it. But the next constellation on this list is stranger for a reason nobody intended, because at some point in the last 100 years, somebody cut it in half. Number 9, Serpens, the constellation that was cut in half. Serpens is the only one of the 88 constellations that exists in 2 disconnected pieces. Not 2 lobes. Not a shape with a narrow waist. 2 separate regions of sky, with a completely different constellation sitting between them. Serpens Caput, the head of the serpent, lies to the west. Serpens Cauda, the tail, lies to the east. Between them, occupying about 20 degrees of sky, sits Ophiuchus, the serpent-bearer, holding the animal in both hands. Together, the 2 halves cover 637 square degrees, which makes Serpens the 23rd largest constellation, and they are administered as a single constellation with a gap in the middle. The figure itself is ancient. It is one of Ptolemy's original 48, catalogued in the 2nd century and inherited from Greek astronomy before that. It is tied to Asclepius, the physician of Greek myth who learned his craft from a serpent and became so good at it that he began raising the dead, at which point Zeus struck him down for upsetting the order of things. The snake and the man have been drawn together in the sky for at least 2,000 years, and in every version of the chart, the man is holding a single continuous animal. The serpent in that story is not decoration. Asclepius learned the art of healing, in the myth, by watching one snake bring a herb to another and revive it. The staff he carried, with a single serpent coiled around it, is still the symbol painted on the side of ambulances and stitched onto the uniforms of medical services in most of the world. A figure from a 2,000-year-old story about the limits of what a physician should be allowed to do is still the working emblem of the profession, and it is also, at the same time, a filing region in the sky. So the strangeness here is not carelessness in the original design. The strangeness is what happened in 1930. When Del Porte drew the official boundaries, he was solving an administrative problem. Astronomers needed to be able to say, without ambiguity, which constellation any given object belonged to. Before the boundaries, different atlases drew the figures differently, and a star could reasonably be assigned to 2 constellations at once. The solution was to abandon the figures entirely as a legal matter and rule straight lines along the coordinate grid instead. It worked. It has worked ever since. There is a consequence of that decision, which still shows up today. Because the boundaries were ruled along the coordinate grid as it stood in 1875, and because the Earth's axis slowly wobbles, the grid has since drifted. The lines are fixed to the stars, but they are no longer aligned with the modern coordinate system. Plot the official constellation boundaries on a current sky chart, and they sit visibly askew, like property lines surveyed from a landmark that has since moved. The sky is divided by a grid that no longer matches the grid it was drawn on, and every astronomer simply works around it. It also meant that when the line was drawn for Ophiuchus, it went straight through the snake. The head ended up in one region, the tail in another, and the middle of the animal became part of the man holding it. Nobody objected, because by 1930, nobody was seriously arguing that the sky contained a snake. The figures had already become a filing convention, and filing conventions do not need to be anatomically coherent. Serpens cauda holds more than the nebula. The Serpens molecular cloud, about 1,300 light-years away, is one of the nearest actively star-forming regions to the Sun. Inside it sits a dense cluster known as Serpens South, discovered by infrared surveys in the 2000s, where stars are forming right now along a filament of cold gas. Some of the objects there are only a few 100,000 years old, which by stellar standards means they are still in the process of switching on. Nearby is W40, a region so heavily obscured by dust that its central cluster could not be properly characterized until infrared instruments were pointed at it. All of this sits in the half of a constellation that was severed from its other half by a boundary line. What the tail half hides is the single most reproduced astronomical image ever made. Messier 16, the Eagle Nebula, sits about 5,700 light-years away in Serpens cauda. It is a large region of glowing gas with a cluster of young, hot stars sitting inside it, perhaps 8,000 of them, all formed within the last few million years. Those stars flood the surrounding gas with ultraviolet light, which is what makes the nebula glow, and which is also, slowly, destroying it. On the 1st of April 1995, Jeff Hester and Paul Scowen of Arizona State University pointed the Hubble Space Telescope at a small region inside that nebula. They assembled 32 separate exposures taken through 4 different filters. What came back were 3 columns of cold molecular gas standing upright against the glare, dense enough to have resisted being blown away and shaped by the erosion happening on every side of them. They are called the pillars of creation. The tallest is about 4 light-years from base to tip, which is very nearly the distance from the Sun to the nearest star. That comparison is worth holding for a moment. Everything humanity has ever built, every probe we have launched, every distance any object of ours has crossed, fits inside a small fraction of the height of one of those columns. The physics of what is happening to them is straightforward and slow. It is called photoevaporation. Ultraviolet light from the young stars above strikes the surface of the gas and gives the outer molecules enough energy to escape. Layer by layer, the surface boils away. Where the gas is thin, it goes quickly. Where the gas is dense, it resists, and the material behind it is shielded, which is why the columns have their shape at all. They are the parts that have not yet been removed. At the tips of the pillars, and scattered along their edges, are small dense knots that Hester named EGGs, for evaporating gaseous globules. Some of them contain forming stars. So the pillars are, in the most literal sense, a nursery being demolished by its own occupants, with the newest occupants sheltering inside the last standing walls. Now hold the image and step inside it. You are standing at the base of one of the columns. Above you, 4 light-years of cold gas rises into a sky that has no ceiling. It is not solid. If you moved into it, you would find nothing to touch, only a slow thickening of the dark, a fog denser than the space around it, but thinner than any vacuum ever made in a laboratory. The light comes from above and behind, hard ultraviolet from a cluster of enormous young stars, and it falls on the top of the column and takes it apart one molecule at a time. You would see the edges glow where the material is being stripped. You would see thin streamers pulled off the rim and drawn away into the wider nebula, moving slowly, the way smoke moves in still air. Nothing here happens quickly. The erosion that shaped this column has been running for hundreds of thousands of years and will run for hundreds of thousands more. And somewhere above you, buried inside the densest knot of the material that has not yet been removed, gas is falling inward under its own weight and beginning to heat, and a star is condensing out of the same substance that is being destroyed around it. The demolition and the construction are the same process. They are simply happening at different densities. The timescales here are worth stating because they set the pace of everything in this nebula. The young stars above the pillars formed a few million years ago. The pillars themselves will be gone within a few 100,000 to a few million years, which sounds slow and is, by the standards of star formation, quite fast. A star like the Sun lives for 10 billion years. The structure that produced these particular stars will not survive 1% of that. The pillars are not a permanent feature of the Eagle Nebula. They are a transient shape that the erosion happens to be making at the moment we arrived to look. And that is the ordinary condition of star-forming regions generally. They are among the most photographed objects in astronomy and among the shortest lived. The gas that made them is dispersed by the stars they produce. The cluster drifts apart, and within a few tens of millions of years, there is nothing left but a loose association of stars moving in roughly the same direction. Almost every star you can see tonight, including the Sun, came out of a structure like this one, and not one of those structures still exists. There is a story attached to the pillars that requires careful handling, because it is widely repeated as fact, and it is not one. In 2007, Infrared data from the Spitzer Space Telescope showed a cloud of hot dust in the region. One interpretation of that dust was the signature of a supernova that had gone off roughly 6,000 years ago, close enough that its shockwave would have already destroyed the pillars, with the news due to reach us in something like another 1,000 years. The idea spread quickly, partly because it is a beautiful and melancholy thought that the most famous structure in astronomy has been gone for millennia, and we are watching a recording. It has never been confirmed. Other readings of the same infrared data do not require a supernova at all. And in October of 2022, the James Webb Space Telescope re-imaged the pillars in the near and mid-infrared and found them standing exactly where they were, with newborn stars visible inside them that Hubble had not been able to see through the dust. That does not settle the question, because the light Webb collected left the region 5,700 years ago regardless. But the supernova claim should be held as an open possibility and not as a finding. The head half of the constellation hides something stranger and far less famous, and nobody has explained it in 76 years. Hoag's object sits about 600 million light-years away in Serpens Caput. It is a nearly perfect ring of blue young stars, 121,000 light-years across, surrounding a compact, round core of old yellow stars, about 17,000 light-years wide. Between the ring and the core is a gap that appears, in visible light, to be empty. Arthur Allen Hoag found it on a photographic plate in 1950. His first thought was that he was looking at an optical illusion. There is a phenomenon called gravitational lensing, in which the mass of a foreground object bends the light of a background object into a ring, and a perfect ring around a compact core is precisely what that produces. If that had been the explanation, the ring and the core would be at completely different distances, and the object would be an artifact of alignment rather than a real thing. Spectra ended that idea. The ring and the core are at the same distance and belong to the same object. Whatever Hoag's object is, it is one galaxy. The ring itself is not uniform. It contains bright knots of star formation, regions where the blue stars are concentrated, which is what you would expect if the ring were the product of a wave of compression rather than a smooth feature. Its stars are a few 100 million years old at most. The core's stars are billions of years old. One object, two entirely unrelated histories, with an apparently empty space between them. The gap is not perfectly empty either. Faint stars have been detected in it. But there are nowhere near enough of them to constitute the disk of a normal galaxy, which is what should be there if this were an ordinary spiral that had somehow been rearranged. The material that should occupy the middle of a galaxy this size is missing, and there is no accepted account of where it went. The leading explanation is a collision more than 2 billion years ago, in which one galaxy passed almost exactly through the center of another. That kind of impact can send a wave of compression outward through a disk, triggering a ring of star formation as it goes, which would account for the young blue stars in the ring and the old ones in the center. The problem is that nobody has found the intruder. There is no debris trail, no disturbed companion nearby, nothing that looks like it took part. Ring galaxies of this kind are rare, and Hoag's object is the most symmetrical example known. And then there is the detail that reads like something the universe left in the file on purpose. In the original images, visible through the gap between the ring and the core, there is a second ring galaxy. A much more distant one, seen by chance through the hole in the first. Serpens Caput carries two other things worth naming. Messier 5 is a globular cluster about 24,500 light-years away, containing roughly 500,000 stars, and at approximately 13 billion years, it is among the oldest objects in the galaxy. It formed before the Milky Way's disk did. It contains at least 100 known variable stars, which is part of why it has been studied so heavily. A globular cluster is a genuinely strange kind of object once you think about what it would be like inside one. 500,000 stars packed into a sphere perhaps 100 light-years across means the stars near the center sit thousands of times closer together than the stars around the sun. From a planet inside one, the night sky would hold thousands of stars, bright enough to cast shadows. There would be no true darkness. Messier 5 has been orbiting the Milky Way in a long, steep loop since before the disk of our galaxy had settled into its present shape, and it has made that circuit many hundreds of times. And Seyfert's sextet is a compact group of galaxies catalogued by Carl Seyfert in 1948. 6 apparent members packed into a region small enough that they appear to be interacting. The reality, established later, is that only 4 of the 6 are genuinely a group. One is a background galaxy at a completely different distance that simply lies along the same line of sight. And one is not a galaxy at all. It is a tidal tail, a stream of stars torn out of one of the real members by the gravity of the others, which looked like a separate object on a photographic plate. Even the groups in this constellation are not what they appear to be, which is a fitting property for a figure that was itself split in two by a committee. There is a thread running through this entry that will run through the rest of the list as well. The pillars of creation are the most familiar image in astronomy. They are on posters, textbook covers, and the walls of classrooms in every country that teaches science. And the square of sky they came from is the one square that the modern system of constellations legally broke into pieces. The most recognizable picture we have of the sky came out of its most damaged file. The next constellation was invented as a joke about a fox, and it is where somebody first heard a dead star keeping time. Number 8. Vulpecula, the little fox that hid the first pulsar. Vulpecula is a small, dim constellation squeezed between Cygnus and the little arrow of Sagitta, and it was invented for no reason more serious than that the space was empty. Johannes Hevelius made it. Hevelius was a brewer and city councillor in Danzig who built one of the finest private observatories in 17th century Europe on the roofs of 3 adjoining houses he owned. He mapped the moon, catalogued stars, and did most of his positional work without a telescope eyepiece at all, using long sighting rules and his own eyes, because he trusted them more than the optics available to him. His star catalogue was among the last great naked-eye surveys ever made, and he was still arguing for the method after telescopic measurement had clearly overtaken it. Hevelius had reason to be careful with his instruments. In 1679, his observatory burned down, taking most of his equipment and a portion of his unpublished work with it. He was 68. He rebuilt, resumed observing, and kept going for another 8 years. The atlas that contains this constellation was assembled from what survived and from what he did afterward, and it was seen into print by his second wife, Elizabeth, who had observed alongside him for decades, and who is one of the first women in the European record to be named as a working astronomer in her own right. He published his atlas, the Firmamentum Sobiescianum, after his death in 1687. In it, he named this patch Vulpecula cum ansere, the little fox with the goose, and drew a fox carrying a goose in its jaws. The placement was a small joke about the neighborhood. The eagle is next door in Aquila. The swan is next door in Cygnus. Hevelius filled the gap between the large birds with a small predator carrying a smaller one, and completed a hunting scene that nobody had asked for. The goose was eventually dropped as a separate figure, and survives now only in the name of the constellation's brightest star, Anser, at magnitude 4.44, an unremarkable red giant about 300 light-years away. The constellation covers 268 square degrees, 55th by area, and it contains nothing that any ancient culture bothered to name. It has no mythology. It is a gap that somebody filled. On the 28th of November 1967, a 24-year-old doctoral student named Jocelyn Bell was working through chart paper at the Mullard Radio Astronomy Observatory in a field outside Cambridge. The instrument she was using was called the Interplanetary Scintillation Array, and she had spent 2 years helping to build it. That is not a figure of speech. The array covered about 4.5 acres. It used more than 2,000 dipole antennas strung on something like 120 miles of wire, supported on more than 1,000 posts, and the construction work involved swinging a sledgehammer in an English field through 2 winters. Bell did that work alongside a small team, and then she operated the finished instrument. Its purpose had nothing to do with what she found. Quasars had been identified a few years earlier as extremely distant, extremely compact sources of radio emission, and it had been realized that because they are compact, their radio signals twinkle as they pass through the turbulent solar wind, in the same way that starlight twinkles through the atmosphere and planets mostly do not. Measuring the twinkling was a way of measuring how compact a radio source was. That was the survey. That was the thesis. The array produced about 96 feet of paper chart recording every day. Not a data file. Paper, printed continuously by pens dragging across a moving roll, which then had to be read. Bell read all of it, by eye, and she read it fast enough to keep up with an instrument that never stopped. Weeks before that November night, she had noticed something. About 1/4 of an inch of what she described as a bit of scruff. It was not the smooth signature of a scintillating quasar, and it was not the sharp mess of terrestrial interference, which she had learned to recognize, and there was a great deal of it, because 1960s England was full of unshielded electrical equipment. What made the scruff worth a second look was that it came back at the same sidereal time. Sidereal time is time measured against the stars rather than against the sun, and a signal that returns on a sidereal schedule is fixed to the sky. It is not a passing car, a faulty thermostat, or a nearby radar. It is up there. On the 28th of November, she ran the chart recorder at high speed over that patch of sky and resolved what the scruff was made of. It was a train of pulses. One pulse every 1.3373 seconds, holding that interval with a precision that rivaled a laboratory clock. Nothing known could do that. The problem was not the pulsing. Stars vary. The problem was the combination of speed and regularity. Anything that flickers on a timescale of a second has to be physically small, because a large object cannot change its output faster than light can cross it. And anything small enough to pulse in 1 1/3 seconds should not have been detectable at interstellar distance in the first place. The signal was demanding 2 contradictory things at once. The team, informally, labeled it LGM-1, Little Green Men 1. That was half a joke, and only half. The possibility that they had picked up a deliberate transmission from another civilization was taken seriously enough to be worrying rather than exciting. Bell has described the reaction with a dryness that has not softened over the decades. She was in the final stretch of a doctorate. She had a thesis to finish. And the most likely explanation for her data, on the evidence available in early December of 1967, was something that would have made the thesis irrelevant and turned her life into something else entirely. Then, later that December, she found a second one. A different part of the sky. A different period. two independent civilizations, broadcasting on the same principle, at the same frequency, to the same telescope, in the same few weeks, was not a plausible universe. It was a natural object, and there were many of them. The paper appeared in Nature in February of 1968. The object is catalogued now as PSR B 1919 plus 21, and it is a neutron star, the collapsed core left over when a massive star exhausts its fuel and its center falls in on itself. It is roughly 20 kilometers across, and it contains more mass than the Sun. It spins, it carries a magnetic field of enormous strength, and it sweeps a beam of radio emission around with it, so that from our position we receive a pulse each time the beam crosses us. It is a lighthouse made out of a dead star, and the reason its timing is so precise is that there is nothing in the universe more stable than the rotation of an object that dense. It is worth being precise about what a neutron star is, because the numbers are the whole point. Take something heavier than the Sun and compress it into a sphere about the width of a large city. The material at the center is denser than an atomic nucleus. A sugar cube of it would weigh about as much as all the people on Earth. The surface gravity is on the order of 100 billion times the Earth's. An object that dense has enormous rotational inertia, which means that once it is spinning, essentially nothing can slow it down quickly, and its rotation becomes a clock more stable than most clocks ever built by hand. The magnetic field is the other half of the mechanism. Collapsing a star's core concentrates its magnetic field along with everything else to strengths 1 trillion times that of the Earth's field. Charged particles are dragged around by that field and radiate along the magnetic axis, which is generally tilted away from the rotation axis. So the emission comes out as two beams, and they sweep. Whether we see a pulsar at all is purely a matter of whether one of those beams happens to cross our line of sight. Most neutron stars in the galaxy are presumably beaming in directions that miss us entirely. The 1974 Nobel Prize in Physics went to Anthony Hewish and Martin Ryle. Bell was not included. She has spoken about it consistently for 50 years, and she has never played the part that people keep offering her. She has said that she does not resent it, that supervisors are the ones who take the risk of setting up a project and should be recognized for it, and that being left out has probably brought her more attention over a longer period than being included would have. She has also, quietly and without making a campaign of it, spent a career opening doors for people who were not expected to be in the room. In 2018, 51 years after the scruff on the chart paper, she was awarded the Special Breakthrough Prize in Fundamental Physics, worth $3 million. She gave every dollar of it away. The whole amount went to fund doctoral scholarships in physics, for women, for refugees, and for students from ethnic minorities, administered by the Institute of Physics. She has said the reason is straightforward. She believes that unconscious bias is the main thing holding back the field, and that the most useful thing to do with $3 million is to put a different set of people in front of the data, which is the thread to keep hold of tonight. Someone had to be looking. The array was built for something else. The signal was 1/4 of an inch of scruff on a roll of paper, and everything we now know about neutron stars follows from one person deciding that a small anomaly on a chart she was tired of reading was worth going back to. The uses that followed are worth listing because they came from a signal nobody was looking for. Pulsar timing produced the first indirect proof that gravitational waves exist, from a binary pair whose orbit was observed shrinking at exactly the rate general relativity predicts if the system were radiating energy away as ripples in space-time. Pulsars were used to find the first planets ever detected outside the solar system, 3 years before the first planet was found around an ordinary star. And the plaques carried by the Pioneer spacecraft locate the Sun by its position relative to 14 pulsars, identified by their periods, on the reasoning that pulsar periods are the one set of numbers any technological civilization anywhere would be able to check. The same constellation hides the object that gave an entire class of nebula the wrong name. On the 12th of July, 1764, Charles Messier was hunting comets, which was his actual profession, and finding faint patches that were not comets, which annoyed him. He catalogued them so that he and others would stop mistaking them for the thing they were looking for. The 27th entry in that catalogue sits in Vulpecula, and it is the Dumbbell Nebula. It is about 1,200 light-years away and roughly 1.5 light-years across, and it was the first planetary nebula ever discovered. The name is a mistake that stuck. William Herschel coined the term decades later because through his telescopes, objects of this type showed small round disks that reminded him of the newly discovered planet Uranus. They have nothing to do with planets. A planetary nebula is the shed outer atmosphere of a dying star of moderate mass, blown off over tens of thousands of years and then lit from inside by the exposed stellar core left behind, which is hot enough to make the escaping gas fluoresce. The dumbbell is about 10,000 years old, expanding at roughly 30 kilometers per second, and the white dwarf at its center is one of the largest known by radius. It will fade to invisibility within a few tens of thousands of years, which is why these objects are rare, despite the process being common. It is also a preview. The Sun will do this. In roughly 5 billion years, it will swell, shed its outer layers over a long, slow exhalation, and leave behind a white dwarf the size of the Earth, surrounded by a glowing shell that will last a geological instant and then disperse. There is a planet here too, and it is one of the most thoroughly studied worlds outside the solar system. HD 189733b orbits an orange dwarf about 64 light-years away, once every 2.2 days, at roughly 1/30th of the distance from the Earth to the Sun. It is a gas giant sitting close enough to its star to be permanently roasted. In 2007, the Spitzer Space Telescope produced the first temperature map of any planet beyond the solar system from observations of this world. In 2013, Hubble measured its actual color by watching the total light of the system change as the planet passed behind its star and subtracting one from the other. The answer was deep cobalt blue. The blue does not come from water. It comes from silicate particles condensing high in an atmosphere at around 1,000 degrees Celsius. Silicate condensing out of vapor is glass. The particles form high in the atmosphere, scatter blue light preferentially, and are driven sideways by winds estimated in the thousands of kilometers per hour. On a world in the little fox with the goose, it rains glass horizontally. The atmosphere of that planet has been taken apart in more detail than almost any other. It was the first exoplanet to have carbon dioxide detected in its air, the first to have a full temperature map, and one of the first to show clear evidence of being stripped, with hydrogen escaping from its upper atmosphere in a stream driven off by the star's radiation. The day side runs hotter than the night side by hundreds of degrees, and the winds that carry heat around the planet run in one direction at speeds no weather system on Earth approaches. And there is a fourth thing here, which is strange precisely because it is not real. The coat hanger, also called Brocchi's cluster, is a line of 6 stars with a hook of 4 rising above it, forming a shape so exact that it looks manufactured. Through binoculars, it is one of the most satisfying sights in the summer sky because it does not require imagination. It simply is a coat hanger. For most of the 20th century, it was catalogued as a genuine open cluster, a group of stars born together from the same cloud. Precise parallax measurements from the Hipparcos satellite in the 1990s ended that. The stars lie at distances ranging from about 200 light-years to more than 1100. They are not related. They were not born together, they are not moving together, and in 100,000 years, the shape will be gone. The most convincing small pattern in this part of the sky is a coincidence, which is, in miniature, the argument of this entire list. What remains genuinely unknown here is more basic than any of it. Nearly 60 years and more than 3,000 known pulsars later, the mechanism that generates the radio beam itself is still not settled. We can time these objects to nanoseconds. We use them to test general relativity to extraordinary precision. Arrays of dozens of them are being used right now as a galaxy-sized detector for gravitational waves passing through the space between us and them. And we still cannot fully explain how the light is made. A graduate student staring at chart paper in a wet Cambridge field found the first proof that dead stars keep time, and the prize went to someone else, which is its own quiet fact about how discovery actually works. And the next entry contains a star that has been watched for 430 years, and which spent 411 of them hiding something 13 light-years long. Number 7. Cetus, the sea monster, with a 13 light-year tail. Cetus is the fourth largest constellation in the sky, and for its size, it looks conspicuously empty. It covers 1,231 square degrees. Only 3 constellations are bigger. It is an ancient figure, one of Ptolemy's original 48, and it represents the sea monster sent by Poseidon to devour Andromeda before Perseus intervened. In some traditions, it is a whale. Its brightest star, Deneb Kaitos, reaches only magnitude 2, which for a region of that extent is thin. A person looking south on an autumn evening sees a large, quiet area of sky with very little in it. It also has a quiet technicality attached to it. Cetus reaches up to the edge of the ecliptic, the path the sun traces through the year, and the moon and the planets sometimes wander across the boundary into it. It is not a zodiac constellation and never has been. It simply touches the road that the zodiac was drawn along, which makes it one of several constellations that the classical scheme ignores, while the actual sky does not. In August of 1596, a Frisian pastor named David Fabricius was watching Mercury. Fabricius was a Lutheran minister in a small town in what is now the northern Netherlands, and he was an amateur astronomer of unusual quality. He corresponded with Tycho Brahe and later with Kepler. He had no telescope because the telescope had not yet been invented. Everything he did with his eyes, a quadrant, and a great deal of patience. To measure Mercury's position, he needed a reference star nearby, and he picked one in Cetus. Over the following weeks, the reference star brightened. That was inconvenient, but not alarming. Then it faded. Then it disappeared entirely from the sky. He assumed he had seen a nova. Novae were known in the sense that a handful had been recorded and argued about, and the standing interpretation was that they were temporary. A star flared once, and it was gone. Tycho had observed one in 1572 and had used it to argue, against 2,000 years of doctrine, that the heavens beyond the moon were not perfect and unchanging after all. 13 years later, in 1609, Fabricius saw the same star again. That single observation did something that Tycho's nova had only begun. A nova that flares and dies can be explained away as an exception, a one-off blemish. A star that fades, returns, fades again, and keeps doing it on a schedule is a different kind of fact. It means change in the heavens is not an accident. It is a behavior. Johannes Holwada established the roughly 11-month cycle in 1638. Hevelius, the same man who invented the little fox, gave the star its name in 1662. He called it Mira, which means the wonderful. Mira varies over about 332 days, from around magnitude 2 at its brightest to around magnitude 10 at its faintest. At maximum, it is roughly as bright as the pole star and perfectly obvious to anyone who looks. At minimum, it needs a telescope. That is a brightness change of something like 1,500 times, running on a cycle slow enough that a person can follow the whole thing with their own eyes across a year without any instrument at all. Mira's maximum is not the same every cycle. Some maxima reach magnitude 2, and some barely get past magnitude 4, and the timing wanders by weeks. That irregularity is part of why it took so long to establish the period at all, and it is also why the star has been followed continuously by amateur astronomers for well over a century. Variable star observing is one of the few areas of astronomy where an ordinary person with binoculars and a chart still contributes usable data, because the work is not about resolution or sensitivity. It is about somebody looking on a particular night. There are more than 400 recorded maxima of Mira, and a great many of them were recorded by people who were not professionals. What is physically happening is that Mira is a red giant near the end of its life, and it is pulsing. The outer envelope expands and contracts. The temperature at the surface changes with it, and crucially, the chemistry changes too. When the star cools, molecules and dust grains condense in its outer atmosphere and absorb a great deal of the visible light. When it heats, they break up again. So the enormous swing in brightness is not mostly the star changing its energy output. It is the star repeatedly building and destroying its own veil. If Mira were placed where the Sun is, its surface would reach out past the orbit of Mars. It is also not alone. There is a companion, Mira B, a white dwarf about 70 astronomical units away. Surrounded by a disk of material, it has stripped off the giant. The two of them have been feeding one into the other for a long time. None of that is the strange part. In 2007, an ultraviolet survey satellite called the Galaxy Evolution Explorer imaged Mira and found something that had never been seen around any star. The Galaxy Evolution Explorer was a modest spacecraft. It launched in 2003. It was about the size of a person, and its job was to survey the whole sky in ultraviolet, a band the atmosphere blocks entirely, and which had therefore been mapped far less thoroughly than visible light or infrared. Mira was not a priority target. It appeared in survey data, and someone noticed that the star had something attached to it. Mira is moving. It travels through the galaxy at roughly 130 kilometers per second relative to the gas around it, which is fast, and it is shedding material continuously as it pulses. Those two facts together do what they would do to any object moving through a medium. Ahead of the star, the interstellar gas piles up into a bow shock, the same shape as the wave at the front of a boat. And behind the star, streaming away, is a tail. The tail is 13 light-years long. That is roughly 3 times the distance from the Sun to the nearest star. It contains material shed over about 30,000 years, laid out behind the star in the order it left, so that the far end of it is a record of what Mira was doing when human beings were painting on the walls of caves in southern Europe. The near end is what it did last century. The material in that tail is not simply gas. Mira is an evolved star, which means the fusion in its interior has been building heavier elements for a long time, and the material it sheds carries carbon, oxygen, and the dust grains that condense out of them. That is the raw stock of everything that comes next. Interstellar dust is where the atoms in rock and water and living tissue spend most of their existence between one generation of stars and the following one. What Mira is doing along that 13 light-year track is delivering, slowly and in a line, the ingredients of some future system that has not begun to form yet. And it is completely invisible in ordinary light. It shows only in the ultraviolet, which is why nobody had ever seen it. Mira has been under continuous scientific observation since 1596. It is one of the most watched individual stars in the sky, with more than 400 recorded maxima. For 411 of those years, nobody knew it had a wake. Fabricius did not live to see any of the argument settled. He was murdered in 1617 by a local man he had accused from the pulpit of stealing a goose, which is an ending nobody would accept in fiction. His son David Fabricius the Younger had by then made his own contribution to the record, having been among the first to observe sunspots with a telescope and the first to describe their motion as evidence that the sun rotates. Between them, in one generation, a country family in the northern Netherlands established that the sun turns and that the stars change. Cetus also hides a galaxy whose center we cannot see and have nevertheless looked directly into. Messier 77, also catalogued as NGC 1068, is a spiral galaxy about 47 million light-years away. Pierre Méchain found it in 1780 and took it for a nebula. It is one of the closest and brightest active galaxies to us, which means its core contains a supermassive black hole actively consuming material and releasing an enormous amount of energy in the process. The problem with this particular galaxy is that its core is wrapped. There is a thick torus of gas and dust surrounding the center, oriented so that we are looking at it edge-on, and it is opaque. Visible light does not get out. Ultraviolet does not get out. Even most X-rays, which pass through a great deal, are absorbed. For decades, NGC 1068 has been the textbook example of an active galaxy we can study only indirectly, by looking at the light it scatters off surrounding material rather than the light from the core itself. There is a reason we can be reasonably confident about the geometry, and it comes from a broad idea called the unified model of active galaxies. The proposal is that the enormous variety of names given to bright galactic cores over the decades, and there are many of them, mostly describes one kind of object seen from different angles. If you are looking down the axis, you see straight into the engine, and it is blindingly bright across the spectrum. If you are looking edge-on through the torus, you see an obscured core and only the light that has scattered off material above and below. NGC 1068 was one of the key objects that built that argument, because polarized light from its core showed the hidden interior reflected off surrounding gas, like seeing a lamp you cannot look at directly by its reflection in a window. In November of 2022, the IceCube Neutrino Observatory reported that it had detected neutrinos coming from it. IceCube is a cubic kilometer of Antarctic ice at the South Pole, threaded with more than 5,000 light sensors buried as deep as 2.5 kilometers. It detects neutrinos indirectly by catching the faint blue flash produced when a neutrino happens to interact with a nucleus in the ice. Neutrinos almost never interact with anything. Hundreds of trillions of them from the Sun pass through every person on Earth every second without effect. That is exactly why they are useful. A neutrino produced in the core of an obscured galaxy is not slowed by the obscuring material, because the obscuring material is not there as far as the neutrino is concerned. The detection was not a single dramatic event. It was statistical. Neutrinos arrive from all over the sky, most of them produced by cosmic rays hitting the Earth's atmosphere, and the task is to find a slight excess coming from one direction after years of counting. That is what happened here, an accumulation, over about a decade, of a modest number of high-energy events pointing back to one galaxy, with the excess strong enough that it was very unlikely to be chance. The result matters beyond this one object. Neutrinos at these energies have to be produced by protons being accelerated and then colliding with something, which means the core of this galaxy is not merely hot. It is a particle accelerator running continuously, and it is hidden behind enough material that we would never have known from its light. About 79 of them, accumulated over roughly a decade of observation, arrived from the direction of this galaxy in Cetus. It was the first time anyone had looked inside the working core of an active galactic nucleus, and it was done with particles rather than with light. 11.9 light-years away, in the same constellation, sits Tau Ceti, the nearest single sun-like star. Most stars near us are red dwarfs, much smaller and cooler than the Sun, and many of the rest are in binary systems. Tau Ceti is neither. It is a single yellow star, somewhat smaller and older than the Sun, and noticeably poorer in heavy elements. And for that reason, it has occupied a permanent place in the imagination of anyone thinking about where to look for company. In April of 1960, Frank Drake pointed the 85-foot dish at Green Bank, West Virginia, at Tau Ceti, and then at Epsilon Eridani, and listened. That was Project Ozma, the first serious radio search for signals from another civilization. He listened for about 200 hours over 4 months, on the frequency of neutral hydrogen, on the reasoning that anyone transmitting deliberately would pick a frequency the whole galaxy agrees on. He recorded one exciting signal that turned out to be a passing aircraft, and nothing else. Drake's search is worth remembering for its modesty. He had a single dish, a receiver built for the purpose, and no institutional permission worth speaking of. He gave the project a name from a fictional queen of a faraway land in an Oz novel, and he chose 2 stars because 2 was what the schedule allowed. It found nothing, and it established the entire method. Every search since has used a version of the same logic. Pick a frequency that physics makes obvious, point at a nearby star like ours, and listen for something that is narrow in frequency and does not look natural. Tau Ceti has since been found to carry a debris disk roughly 10 times denser than the Sun's Kuiper belt, along with 4 or 5 planet candidates that remain contested. A dense debris disk means a great many collisions and a great deal of material still falling inward. If anything lives there, it lives somewhere considerably rougher than here. And then there is the last thing in this constellation, which is not a thing at all. In 2017, a team led by Yehuda Hoffman, working with Daniel Pomerade and Brent Tully, mapped the velocities of thousands of nearby galaxies. Rather than plotting where galaxies are, they plotted where galaxies are going, and then worked backward to the distribution of mass that would produce those motions. We know we are moving because of the cosmic microwave background. The oldest light in the universe fills the sky almost perfectly evenly, and the largest departure from evenness is a simple lopsidedness, slightly warmer in one direction, slightly cooler in the opposite one. That pattern is a Doppler shift, and it is the signature of our own motion through the light. It tells us we are moving at roughly 630 kilometers per second, and it tells us the direction. What it does not tell us is why. Working that out means mapping the mass around us, and the surprising part of the answer is that a share of the effect comes not from what is pulling, but from where there is nothing to pull. The map showed a large, underdense region, roughly opposite the direction of the great attractor on the sky, in the direction of Cetus. They named it the dipole repeller. An empty region has no gravity of its own to give. But gravity is relative, and if you sit between a dense region on one side and an unusually empty one on the other, the net effect is that you are pulled toward the dense side and, in practical terms, pushed away from the empty one. Part of our own galaxy's motion through the universe appears to come from being shoved by nothing at all. The nothing is in the sea monster. The star that first taught human beings that the sky is allowed to change was found by a village pastor with no instrument at all, and 4 centuries later, the same star was still holding back a secret 13 light-years long. But the next constellation on this list hides something we could not see at all until we learned to look in colors our eyes do not have. Number 6. Sagittarius, the teapot over the center of the galaxy. Sagittarius is the archer, and almost nobody has ever seen an archer in it. It is one of Ptolemy's original 48 and one of the 12 zodiac constellations, covering 867 square degrees, 15th by area. The classical figure is a centaur drawing a bow. What people actually see, and what every practical observing guide now tells them to look for, is a teapot. 8 stars form a body, a handle on the left, a lid on top, and a spout on the right. Rising from the spout is the brightest, densest section of the Milky Way visible from Earth, which looks precisely like steam. That is not a coincidence of shape. It is a coincidence of direction. When you look at Sagittarius, you are looking toward the center of our own galaxy, and therefore through the greatest depth of stars available in any direction from here. This is why Sagittarius holds 15 Messier objects, more than any other constellation. It is the richest patch of sky in the catalogue because it is the direction with the most stuff behind it. The 15 Messier objects are worth naming because they are the reason this constellation is where every summer observing session in the northern hemisphere ends up. The Lagoon Nebula, a star-forming region so large and bright that it is visible without optical aid from a dark site. The Trifid, split into 3 lobes by dust lanes. The Omega, sometimes called the Swan. Globular clusters, including Messier 22, which is one of the brightest in the entire sky and one of the first ever discovered. All of them lie between us and the center, in the thick of the disk, which is exactly why there are so many of them in one place. And the strangeness of this constellation is not that it is arbitrary. It is that the single most important object in our galaxy sits inside it, and for the entire history of astronomy, nobody could see it. The line of sight to the galactic center passes through an enormous quantity of interstellar dust. The dimming is on the order of 30 magnitudes at visible wavelengths, which is a factor of roughly a trillion. If the center of the galaxy were unobscured, it would be one of the brightest things in the night sky. Instead, it is behind a curtain that no optical telescope of any size can penetrate. Everything we know about what is there was learned in radio and in infrared, wavelengths that pass through dust and which human eyes do not have. Dust is worth understanding properly because it is the reason for a large share of what this list contains. Interstellar dust grains are tiny, on the order of a fraction of a micron, and they are not evenly spread. They collect in the plane of the galaxy, in the same disk where the stars and gas are, which means that looking along the plane means looking through the maximum possible amount of it. Dust absorbs and scatters short wavelengths far more effectively than long ones, which is why obscured regions look red and why infrared and radio get through when visible light does not. It is the same physics that makes a sunset red, operating over 26,000 light-years instead of a few hundred kilometers of air. What is there is a black hole of about 4.3 million solar masses, 26,000 light-years away, catalogued as Sagittarius A star. Its event horizon is roughly 24 million kilometers across, which would fit comfortably inside the orbit of Mercury. That is not large by the standards of black holes, and it is worth saying plainly that 4 million solar masses is on the modest end for the center of a galaxy of this size. Our black hole is also unusually quiet. It consumes very little material compared to what models once assumed a galactic center should be doing, and if it were switched on properly, life on the inner disk of this galaxy would be a considerably different proposition. Measuring it took 30 years of watching individual stars. Beginning in the early 1990s, two independent teams took on the same problem from opposite sides of the world. One was led by Reinhard Genzel in Germany, working with telescopes in Chile. The other was led by Andrea Ghez in California, working with the Keck telescopes in Hawaii. Both were doing infrared astronomy at the limit of what was possible, using techniques that correct for the blurring of the atmosphere in real time, and both were doing the same thing, tracking the positions of individual stars in the crowded region at the galactic center, year after year, and waiting to see whether they moved. The technique that made it possible is called adaptive optics, and it is one of the quiet triumphs of the last 40 years. The atmosphere blurs starlight because pockets of air at different temperatures bend light by different amounts, and those pockets move. Adaptive optics measures that blurring hundreds of times per second, usually against a bright reference star or an artificial one made by shining a laser into the sodium layer of the upper atmosphere, and then deforms a small mirror in the light path to cancel it out. The result is a ground-based telescope producing images nearly as sharp as one in orbit. Without it, the individual stars at the galactic center would remain a single smear, and the orbits could never have been measured. They moved. They moved on ellipses, around a common focus, with nothing visible at that focus at all. The star known as S2 became the key. It completes a full orbit every 16 years, which is short enough that a single research career can watch several. At its closest approach, it comes within about 120 astronomical units of the black hole, and at that point it is traveling at roughly 3% of the speed of light. From the shape and speed of that orbit, the mass at the focus can be calculated the same way the mass of the Sun is calculated from the orbit of the Earth. The answer was 4 million times the Sun, in a volume small enough that nothing else known could produce it. The orbit of S2 also did something more than weigh the black hole. In 2018, as the star made its closest approach, the teams measured its light and found it shifted toward the red by exactly the amount general relativity predicts for light climbing out of a gravitational well that deep. 2 years later, they measured the slow rotation of the orbit itself, the precession that Einstein's theory requires and Newton's does not. The same effect, on a far smaller scale, was the first observational success of general relativity a century earlier, measured in the orbit of Mercury. The test was repeated at the center of the galaxy, against a black hole, and the theory held. Genzel and Ghez shared the 2020 Nobel Prize in Physics for that work. Ghez was the fourth woman ever to receive it. On the 12th of May, 2022, the Event Horizon Telescope collaboration released the first direct image of the shadow itself. The image was assembled from observations made in April of 2017 by 8 radio observatories spread across the Earth, from Hawaii to Chile to the South Pole, all recording at once and functioning as a single instrument the size of the planet. There was so much raw data that it could not be transmitted. It had to be flown on hard drives to central processing sites. It took 5 years to turn into a picture, and the picture is a ring of light around a dark center, exactly the size that general relativity says it should be. The same constellation holds the most famous unexplained signal in the history of radio astronomy. On the 15th of August 1977, the Big Ear radio telescope at Ohio State University recorded a narrowband burst at about 1420 megahertz. That frequency is not arbitrary. It is the emission line of neutral hydrogen, the most common substance in the universe, and it has been proposed since the 1950s as the obvious channel for anyone attempting to be heard across interstellar distance, on the grounds that every civilization with radio astronomy will already be watching it. The choice of hydrogen's frequency has a name in the literature. It is sometimes called the water hole because the emission lines of hydrogen and the hydroxyl radical sit close together in the radio spectrum, and hydrogen plus hydroxyl makes water. The region between them is quiet, natural background is low, and the metaphor of a watering hole where different species meet has proved impossible for anyone in the field to resist. Whether that reasoning would occur to a mind that did not evolve on a planet covered in water is a question nobody can answer, and it is a fair criticism of the whole approach. Big Ear was an unusual instrument. It was the size of 3 football fields, and it could not be steered. It had a fixed flat reflector and a fixed curved one, and it observed by letting the Earth's rotation carry the sky through its beam. There was no observer on duty. The telescope printed its output onto continuous paper, and somebody read the paper later. Stand in that room for a moment. It is the middle of the night in Ohio, and there is nobody in the building. Outside, an enormous metal structure sits in a field, pointing at nothing in particular, because it cannot point. The sky moves across it. A printer runs. Numbers and letters appear on a roll of paper at a steady rate, most of them the background hiss of the universe, and nothing about the room registers that anything has happened. Somewhere above the roof, a narrow signal at the hydrogen frequency rises into the beam, climbs for 36 seconds, reaches an intensity roughly 30 times the background, and falls away over the following 36. 72 seconds, from nothing to nothing. That is exactly how long a fixed point in the sky takes to drift through this telescope's field of view, which means whatever produced it was not on Earth, was not in orbit, and was holding still against the stars. Then the sky carries it out of the beam, the printer goes back to hiss, and the paper keeps rolling for several more days before anyone reads it. The person who read it was a volunteer named Jerry Amon, going through the printout at his kitchen table. The intensity scale on the printout was compressed into single characters, digits for the low values, and letters for the high ones, so that a whole night could fit on a manageable width of paper. He found the sequence 6EQUJ5. The letter U was the highest single-channel value that survey had ever recorded. He circled it in red pen and wrote one word in the margin. Wow. It has never been seen again. Big Ear itself reobserved that position more than 50 times. Later searches have used instruments far more sensitive, and the region has been examined repeatedly for half a century by people who would very much like to find it. Nothing. It is also worth saying what the wow signal was not. It was not a repeating pattern, it was not modulated in any way that could carry information, and it was recorded on a single instrument with no independent confirmation. What makes it durable is its narrowness in frequency, which natural sources rarely produce, and the fact that it drifted with the sky. Those two facts together are what have kept it in the literature for 50 years, rather than in the discard pile with the thousands of other unexplained blips that every radio observatory generates and forgets. In 2024, a group working with archival data proposed a natural mechanism. A sudden burst of radiation from a magnetar, a neutron star with an extreme magnetic field, could briefly stimulate a cloud of cold hydrogen gas into emitting a narrow, bright beam, in the same way a laser is stimulated in a laboratory. That would explain the frequency, the narrowness, and the fact that it never came back. It is a plausible idea. It is not a settled answer, and the honest position is that we do not know what the wow signal was. The signal came from the direction of the star Chi Sagittarii. The Big Ear was demolished in 1998 to make room for the expansion of a golf course. There is also an entire galaxy in Sagittarius that nobody noticed until 1994. Rodrigo Ibata, Jerry Gilmore, and Mike Irwin were working through survey data, studying the motions of stars in the galactic bulge, and they found a population moving together at the wrong velocity. Not a cluster, not a stream of local stars. A dwarf elliptical galaxy, about 70,000 light-years away, on the far side of the galactic center, being pulled apart by the gravity of the Milky Way. At the moment of its discovery, it was the closest known galaxy to our own. It had hidden for the entire history of astronomy behind the crowded, dust-choked starfields of the bulge, which is the single worst place in the sky to try to notice anything faint. The only reason it was found at all is that velocity measurements can separate objects that images cannot. The discovery changed the picture of our galaxy in a way that is easy to understate. Before 1994, the Milky Way was generally described as a large spiral with two prominent companions and a handful of small ones. After it, the picture became something closer to a galaxy that is continuously eating. Dozens of dwarf galaxies are now known to orbit ours, many of them found by the same technique of looking for stars that move together rather than stars that look grouped, and several of them are visibly being taken apart. The halo of our galaxy is threaded with the stretched remains of things it has already finished consuming. Its debris now wraps in a stream that goes all the way around the Milky Way, and there is a serious body of work arguing that its repeated passages through our disk have triggered waves of star formation in our own galaxy. One of those passages lines up, within the uncertainties, with the formation of the Sun. Two more things belong here. Near the galactic center sits Sagittarius B2, a molecular cloud of about 3 million solar masses, spanning perhaps 150 light-years, and it is the single richest chemical laboratory known to radio astronomy. A great many of the roughly 300 molecules identified in interstellar space were first detected in this one cloud. Among them is ethyl formate, which is the ester responsible for the flavor of raspberries and part of the smell of rum. Also propyl cyanide. Also glycolaldehyde, a simple sugar and a step on the road to ribose, which is the backbone of RNA. And in 2010, a team analyzing data from the Fermi Gamma Ray Space Telescope did the unglamorous work of modeling and subtracting the diffuse gamma ray glow of the galactic plane properly to see what was left underneath. What was left underneath was two enormous lobes of emission, one above the galactic center and one below, each extending about 25,000 light-years. 50,000 light-years from tip to tip. They are called the Fermi bubbles, and they are the fossil of some very large outburst from the region around Sagittarius A star a few million years ago. The Fermi bubbles are large enough that if human eyes could register gamma rays, they would span roughly 30 degrees of the sky, which is about 60 times the width of the full moon. They would be one of the most obvious features of the night. Instead, they went unrecorded until somebody wrote better software for subtracting the foreground, and the discovery consisted of looking again at data that had already been collected and released. What produced them is still argued. One family of explanations has Sagittarius A star swallowing a large quantity of material a few million years ago and driving an outflow. Another has a burst of star formation near the center, with the combined winds and supernovae of many massive stars doing the work. The timing is loosely constrained, and the energy involved is enormous either way. Whatever happened, it happened long after the first primates appeared on Earth, and nothing on Earth recorded it. They had been sitting in the data the entire time. They were invisible only because of what was in front of them. Everything our species has ever done has happened inside a galaxy whose own center we could not see until we learned to look in wavelengths we do not have eyes for, and the first thing we found there was a hole 4 million times heavier than the Sun. The next constellation is fainter than almost any other, and it is the clearest window out of our galaxy that exists. Number 5. Coma Berenices, a queen's hair, and the first evidence of dark matter. We are halfway down the list, and it is worth taking one short look back before we continue. We began with the faintest square in the sky, drawn by a surveyor as a joke about the weather on a mountain in Cape Town, and found a galaxy sitting on it. We went to the only constellation that was legally cut in half, and found the most reproduced image in astronomy inside it. We went to a fox that a brewer invented to fill a gap, and found the first pulsar. We went to a sea monster and found a star with a 13 light-year wake. And we went to the Teapot and found the center of the galaxy behind a curtain of dust. Every one of those was a mismatch between a square of sky and its contents. From here, the mismatches get larger, and they stop being about individual objects. Coma Berenices is the only constellation in the modern 88 named after a real, historically documented human being. Around 243 years before the Common Era, Berenice II was Queen of Egypt, married to Ptolemy III. Her husband went to war in Syria. She cut off her long hair, which was apparently famous, and dedicated it in a temple as an offering for his safe return. The hair disappeared from the temple overnight. This was an awkward situation for everyone. The court astronomer, a Greek named Konon of Samos, resolved it by announcing that the gods had been so pleased with the offering that they had placed the queen's hair in the sky, and he pointed at a faint shimmer of stars near the tail of Leo. We know this story because the poet Callimachus wrote it down, and because the Roman poet Catullus translated Callimachus into Latin, and Catullus survived. The Greek original did not. The origin of a constellation reaches us only as literature, preserved in translation, in a poem numbered 66 in a collection that has nothing else to do with astronomy. Berenice herself did not have a gentle ending. She was murdered some years later in a palace matter involving her own son, in the way that Ptolemaic succession disputes generally resolved themselves. The dynasty she belonged to ended within 2 centuries. The constellation named after an offering she made has now outlasted the kingdom, the temple, the language the poem was written in, and the original poem itself, and it is still on every star chart printed anywhere in the world. For centuries afterward, it was not treated as a constellation in its own right. It was an asterism, a recognized shape without official status, generally described as the tuft at the end of the lion's tail. It became a formal figure through 16th century mapmakers and, decisively, through Tycho Brahe's star catalogue of 1602. It covers 386 square degrees, 42nd by area. Its brightest star is magnitude 4.26, which puts it in the small group of constellations containing no star brighter than 4th magnitude. What the eye actually sees, on a dark night, is not really stars at all. It is the Coma star cluster, several dozen stars about 280 light-years away, one of the nearest open clusters to the Sun, spread loosely enough across several degrees of sky that they genuinely resemble strands rather than points. It is about 450 million years old and slowly coming apart, as all open clusters do. The cluster is a pleasant thing to know about because it is one of the few objects that looks better without a telescope than with one. It is too spread out for most instruments to frame. Binoculars show it well. The unaided eye, from a properly dark sight, sees a soft, irregular scattering that is genuinely hard to describe as anything other than loose hair, which suggests that whoever first attached the story to this patch of sky had actually looked at it. The reason this faint patch matters is geometry. Our galaxy is a disk. We are inside it, near the middle of its thickness, and everything we look at is seen through some amount of that disk. Looking along the plane, as we did towards Sagittarius, means looking through the maximum possible depth of gas and dust. Looking perpendicular to the plane means looking through the minimum. The North Galactic Pole, the direction exactly perpendicular to the plane of the Milky Way, sits inside Coma Berenices. Looking at this constellation means looking straight up out of our own galaxy, through the shortest available path of obscuring material. It is the clearest window out that exists. That is why a constellation with almost nothing in the foreground turns out to be crowded with distant galaxies, and why it contains 8 Messier objects, nearly all of them external systems. Through that window lies the Coma cluster. Catalogued as Abel 1656, it contains more than 1,000 bright galaxies and probably more than 10,000 in total, sitting about 320 million light-years away, bound together in a common cloud of gas at around 100 million degrees. It is one of the most thoroughly studied structures in the universe, and it has been studied for almost a century because it is bright, rich, and sitting in the one direction where nothing is in the way. In 1933, Fritz Zwicky looked at it and did an arithmetic problem. Zwicky was a Swiss-born astronomer at Caltech, difficult, brilliant, and largely disliked by his colleagues, and he was correct about an unusual number of things decades before anyone agreed with him. In the following year, with Walter Baade, he coined the word supernova and proposed that supernovae leave behind neutron stars, which was regarded as fantasy at the time and is now standard. The arithmetic he did on the Coma cluster was standard mechanics. He measured how fast the cluster's galaxies were moving relative to one another, using their spectra. Then he applied a relation called the virial theorem, which connects the average motion of objects in a bound system to the total mass holding them together. It is not exotic physics. It is the same reasoning that lets you weigh the sun from the speed of the Earth. It is worth spelling out why that reasoning is trustworthy, because a great deal rests on it. A bound system settles into a balance between motion and gravity. Objects moving too fast escape. Objects moving too slow fall inward and speed up. Over time, what remains is a population whose typical speed reflects the total mass holding it. That relation is robust. It does not depend on knowing what the mass is made of, where exactly it sits, or whether it emits light. It only requires that the system has been together long enough to settle. The Coma cluster, at 320 million light-years and billions of years old, has certainly settled. The answer did not work. The galaxies were moving far too quickly to be held by the mass that was visible. All the stars in all those galaxies fell short by a large factor, and at the cluster's measured speeds, it should have flown apart long ago, and it plainly had not. His conclusion was that the cluster contains a great deal of matter that emits no light at all, and he gave it a name in German, dunkle Materie. Dark matter. The gas is worth a moment on its own, because it was not known about in Zwicky's time, and it did not solve his problem. X-ray telescopes, beginning in the 1970s, found that clusters like Coma are filled with an enormous quantity of thin, extremely hot gas at temperatures around 100 million degrees, glowing steadily in X-rays. That gas outweighs all the stars in all the cluster's galaxies combined by a factor of several. When it was discovered, there was a reasonable hope that this was the missing mass. It was not. Add the gas to the stars, and the cluster is still short by a large factor. The visible universe, in every form we can detect it, is roughly a sixth of what the gravity requires. The idea was almost entirely ignored for about 40 years. Part of that was Zwicky himself, whose relations with the profession were poor. Part of it was that the measurement was difficult and the uncertainties were real. And part of it, honestly, is that a result which says most of the universe is missing is easier to set aside than to act on. The idea was revived in the 1970s when Vera Rubin and Kent Ford measured how fast stars orbit within individual spiral galaxies and found that the outer stars move much faster than the visible mass allows, in galaxy after galaxy after galaxy. That was a completely different kind of system and a completely different measurement, and it produced the same discrepancy. The lensing evidence deserves mention because it is the most direct. Mass bends light. A cluster with enough mass in it will distort the images of galaxies behind it, stretching them into arcs. And from the pattern of the distortion, the mass distribution can be mapped without any assumption at all about motion or equilibrium. Those maps agree with the dynamical measurements. They also show that the mass is not where the light is. It is spread more broadly, in a large halo that the galaxies move within, which is exactly what a cloud of non-luminous particles would produce, and exactly what a simple error in the visible mass accounting would not. 93 years after Zwicky's calculation, dark matter is understood to make up roughly 5 times as much mass as ordinary matter. Its gravitational effects are seen in galaxy rotation, in cluster dynamics, in the way clusters bend the light of things behind them, and in the pattern of the oldest light in the universe. It has never been directly detected. Every candidate particle proposed for it has so far failed to appear in any experiment built to find it, and several generations of increasingly sensitive detectors have now been built and have found nothing. What dark matter might actually be is a question that has been narrowed rather than answered. The leading class of candidate for decades was a heavy, slow-moving particle interacting only through gravity and the weak nuclear force, and detectors were built deep underground, shielded by kilometers of rock, waiting for one to nudge a nucleus. Those detectors have improved in sensitivity by many orders of magnitude and have seen nothing. Other candidates remain open, much lighter particles, particles that interact even more feebly, or a large population of black holes formed in the first moments of the universe. There are also serious researchers who argue that the discrepancy is telling us our theory of gravity is incomplete on galactic scales, rather than that there is unseen matter, though that position has grown harder to hold as the evidence has accumulated from independent directions. What is not in doubt is the discrepancy itself. It shows up in the rotation of individual galaxies, in the motion of galaxies within clusters, in the bending of light around those clusters, in the pattern of temperature variations in the oldest light in the universe, and in the way the largest structures grew from nearly uniform beginnings. 5 independent lines of evidence, from 5 different kinds of measurement, all requiring roughly the same amount of something that does not shine. The first evidence for the substance that dominates the matter content of the universe was found by looking through a constellation named after a woman's hair. The same cluster contains one of the largest black holes ever weighed. NGC 4889 is a giant elliptical galaxy near the cluster's center, and estimates of its central black hole run to around 21 billion solar masses. Its event horizon would be something like 130 billion kilometers across, about 12 times the diameter of Neptune's orbit. It did not grow that way by accident. Galaxies at the centers of rich clusters grow by consuming other galaxies, and every galaxy consumed brings its own central black hole, which eventually settles to the middle and merges. That number is an accumulation of hundreds of smaller ones. There is one more galaxy here worth naming, and it is a small mystery in its own right. Messier 64, generally called the Black Eye Galaxy, has a thick dark band of dust across the front of its bright core, which is where the name comes from. The interesting part is not the dust. It is that the gas in the galaxy's inner region rotates in one direction, and the gas in the outer region rotates in the opposite direction, with a boundary of about 3,000 light-years between them. That configuration cannot arise naturally in a single galaxy. It is the fossil of a merger, in which a smaller galaxy fell in on a retrograde orbit, and its gas was absorbed without ever agreeing to turn the same way as the host. And in 1989, Margaret Geller and John Huchra found something in the same direction that changed the shape of the universe. They were running a redshift survey, measuring the spectra of galaxies one at a time to get their distances, and building a three-dimensional map rather than a picture. 15,000 galaxies, one spectrum at a time, over years. When they plotted the result, the galaxies were not scattered evenly. They lay in a sheet. The method mattered as much as the result. Taking a picture of the sky gives you two dimensions. Everything is projected onto the same surface, and a galaxy 10 million light-years away sits next to one 500 million light-years away with nothing to distinguish them. A redshift survey adds the third dimension, one object at a time, by measuring how much each galaxy's light has been stretched by the expansion of the universe and converting that into a distance. It is slow, unglamorous, and it produced the first real map of anything larger than a cluster. Every large-scale structure known today descends from that technique. The structure is called the Great Wall. It is roughly 500 million light-years long and 300 million wide, but only about 15 million thick, and it is centered on the Coma cluster. At the time of its discovery, it was the largest known structure in the universe, and it ended the working assumption that the universe is smooth if you zoom out far enough. It is not smooth at that scale. It is filaments and sheets and empty space, and everything sits on the edges of the emptiness. The wall is not alone either. Larger structures have been mapped since, and the general picture that emerged is called the cosmic web, galaxies strung along filaments, filaments meeting at clusters, and between them enormous regions with almost nothing in them at all. Most of the volume of the universe is in the empty parts. Most of the matter is on the boundaries. The Coma cluster sits at a junction of that structure, which is another reason it is so rich, and the clear window we happen to have in this direction is what allowed the pattern to be noticed from here at all. There is a last, quieter thing in that cluster. Hubble observations found stars drifting between the galaxies, belonging to no galaxy at all. Something like 1 trillion of them, spread through the cluster volume, orbiting the cluster as a whole. They are the stripped remains of everything the cluster has taken apart over billions of years, and they are, collectively, a substantial fraction of all the starlight in the system. A Queen's offering became the one square of sky through which we can see straight out of our own galaxy, and the first thing anyone found looking through it was that most of the universe is made of something we still cannot name. And the next constellation had its 2 brightest stars legally taken away, which turns out to be the least strange thing about it. Number 4, Norma, the Carpenter's square that hides what we are falling into. Norma is another of Lecaille's 14 inventions from the Cape, and it is named after a tool. The original title was L'équerre et la règle, the set square and the rule. A set square is the right-angled triangle a draftsman uses to draw perpendicular lines, and a rule is a straight edge. Together, they are the instruments of making something square. Lecaille put them in the sky between the Scorpion and the Centaur, alongside his air pump, his level and his compass, and the name was later shortened to Norma, which in Latin means a carpenter's square, and by extension, a standard or a rule. It is the root of the word normal. Lacaille's instrument Constellations have never been popular, and it is easy to see why. A hero with a sword is memorable. A set square is not. Several of them were later trimmed or absorbed, and the ones that survive tend to be the faintest and least visited regions of the southern sky. But there is something worth respecting in the choice. Lacaille was mapping the sky with instruments in a century that had just worked out that instruments were how you found things out, and he filled the last unnamed part of the heavens with the tools of the trade rather than with more kings and animals. The southern sky is the only part of the celestial sphere named after the 18th century's actual idea of itself. The constellation covers 165 square degrees, which puts it 74th out of 88 among the 10 smallest. It contains no star brighter than magnitude 4. It also has a bureaucratic peculiarity that no other constellation quite matches. Norma has no alpha star and no beta star. The convention for naming stars was set by Johann Bayer in 1603. Within each constellation, label the stars with Greek letters, roughly in order of brightness. Alpha is the brightest, beta the next, and so on down. Lacaille assigned Greek letters to Norma's stars in the ordinary way when he created it. Then came 1930 and the boundaries. When Delporte ruled the lines, the border with Scorpius was drawn in such a way that Norma's alpha and beta ended up on the wrong side of it. They became stars of Scorpius, and they were relabeled accordingly. Nobody went back afterward to promote the remaining stars into the vacancy. So the brightest star in Norma today is Gamma 2 Normae at magnitude 4.0, and there is nothing above it. The alphabet in this constellation begins at the third letter. It was legally stripped of its 2 best stars by a boundary commission and never compensated. That is the surface strangeness, and it is a good story. The real one is what is behind it. Norma sits deep inside the zone of avoidance. The zone of avoidance is the band across the sky where our own galaxy blocks the view of everything beyond it. The disk of the Milky Way is full of stars, gas, and dust, and looking through the plane of it at visible wavelengths means looking through so much material that essentially nothing external gets through. At optical wavelengths, that band covers about 20% of the sky. For most of the history of extragalactic astronomy, it was simply a hole in the map. Galaxy catalogues stopped at its edges and resumed on the other side. The working assumption, which nobody stated because nobody thought it needed stating, was that whatever lay behind the curtain resembled what lay on either side of it. It does not. Through the 1970s and 80s, a group of 7 astronomers set out to measure distances to galaxies independently of their redshifts. They were Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Terlovich, and Gary Wegner, and they became known in the field as the 7 Samurai. Their method used a newly calibrated relationship between an elliptical galaxy's size, its surface brightness, and the speed at which its stars move internally. Measure 2 of those and you can infer the galaxy's true size, and comparing true size to apparent size gives you a distance. That mattered because it gave 2 independent numbers for the same galaxy. The redshift tells you how fast a galaxy is receding. In a smoothly expanding universe, recession speed is proportional to distance, so redshift and distance should agree. Where they disagree, the difference is the galaxy's own motion through space, on top of the expansion. It is worth being clear about what a bulk flow means, because it is a stronger claim than it sounds. Individual galaxies move. That is expected. Gravity pulls on everything, and every galaxy has neighbors. What the Seven Samurai found was not individual motion, but agreement. Galaxies separated by hundreds of millions of light-years, with no way to influence one another on any reasonable timescale, were moving in the same direction at similar speeds. Agreement on that scale can only be produced by something much larger than any of them, pulling on all of them at once. The size of the flow is a measurement of the size of the mass making it. The result was not welcomed immediately. A coherent motion of that scale sat awkwardly with the assumption that the universe is uniform if you average over a large enough volume, which is one of the foundations of modern cosmology. The measurements were difficult, the uncertainties on individual galaxy distances were substantial, and it took years of independent work before the flow was regarded as established rather than as a possible systematic error in a hard technique. They measured hundreds of elliptical galaxies and found that the disagreements were not random. Across an enormous volume of space, galaxies were streaming in the same direction. Not scattered motions in all directions, as you would expect from local gravitational tugs, but a coherent flow. Our own galaxy, the entire local group, and thousands of other galaxies over hundreds of millions of light-years were all moving together toward a common point at several hundred kilometers per second. Measured against the cosmic microwave background, which provides the only reference frame the universe offers, the local group is moving at roughly 630 kilometers per second. That is about 2 million kilometers per hour. The direction was behind the Milky Way's dust, toward Norma. They called the thing at the end of it the Great Attractor. Sit with that for a moment, because it is the plain statement of an ordinary condition that nobody feels. The Earth turns and carries you at 1,000 kilometers per hour at the equator. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the center of the galaxy at about 230 kilometers per second and takes something like 230 million years to complete a circuit. And the whole galaxy, with everything in it, including every person who has ever lived, is falling at 630 kilometers per second toward a point that no human being has ever seen directly, and has been doing so for the entire history of the species, and for the entire history of the Earth, and for a good deal longer than that. There is no sensation of any of it. There cannot be. Motion at constant velocity produces no feeling whatsoever, which is why it took until the 17th century for anyone to work out that the ground is moving at all. What we are doing is not frightening. It is simply the condition, and it was never going to ask. There is a version of this that is easier to picture. Imagine standing on a hillside in fog so thick that you cannot see more than a few meters. You cannot see the valley. You cannot see the ridge on the far side. But you can feel that the ground under your feet slopes, and if you set a ball down, it rolls. And by watching enough balls roll, you can reconstruct the shape of the whole landscape without ever seeing any of it. That is what mapping galaxy velocities does. The Great Attractor was found by watching which way things rolled. For years, nobody could see what we were falling toward. The direction was the worst possible one. Radio surveys changed the picture more than anything else. Neutral hydrogen emits at a wavelength of 21 centimeters, and at that wavelength, the dust of our own galaxy is essentially transparent. A galaxy behind the plane still shows its hydrogen signal, and the signal carries a velocity, which means both a detection and a distance in a single measurement. Systematic hydrogen surveys through the zone of avoidance have reduced the blind band from about 20% of the sky to a few percent. It has never been reduced to zero because directly toward the galactic center, the foreground is simply too crowded, and a small region of the extragalactic universe remains genuinely unmapped. Then, in the 1990s, Surveys designed specifically to see through the galactic plane went to work. Infrared, which penetrates dust. Radio observations of neutral hydrogen, which the dust does not touch at all. And painstaking optical work in the gaps between foreground stars. What they found, sitting almost exactly where the flow pointed, was a massive galaxy cluster. Abell 3627, now called the Norma Cluster, about 220 million light-years away, with a mass on the order of 1,000 trillion suns. That is comparable to the Coma cluster we were just looking at, and it makes it one of the 10 most massive clusters known. It had gone entirely unnoticed until the 1990s. The Norma cluster is not the whole answer either. It is massive, and it is close to the direction of the flow, but by itself, it does not have enough mass to account for the full motion. The current picture is of a broad concentration of mass in that general region, of which the Norma cluster is the densest visible part, embedded in a larger pull from further away. What was called the Great Attractor in the 1980s has since become less a single object and more a name for the bottom of a slope, with the slope continuing well beyond it. The largest single object in our cosmic neighborhood was hidden by the neighborhood we live in. That is the second appearance of the point this list keeps making, and it is a sharper version of it than the first. Mensa was faint because nothing bright happened to be nearby. Norma looks empty because something is in front of it, and the something in front is our own galaxy. Emptiness is never a measure of what is there. Sometimes it is a measure of where you are standing. The Norma cluster has a further detail that gives away how violent an environment it is. It contains a wide-angle tail radio galaxy, which is a galaxy whose central black hole is launching two jets that ought to be straight and are instead swept backward into a V shape. Nothing is bending them mechanically. The galaxy is moving through the cluster gas fast enough that the gas pushes the jets behind it, the way smoke from a moving chimney lies down in the direction of travel. That shape is a direct visual record of motion through a medium, and it is one of the ways astronomers identify clusters that are still actively assembling rather than settled. Inside that cluster is a galaxy being taken apart in a way that is worth stopping to see properly. ESO 137-001 is a spiral galaxy falling into the Norma cluster at high speed. Clusters are not empty between their galaxies. They are filled with that thin 100-million-degree gas, and to a galaxy moving through it at thousands of kilometers per second, that thin gas behaves like a wind. Ride alongside it for a moment. You are moving inward, and the cluster is filling the sky ahead of you. The gas you are passing through is so thin it would count as a laboratory vacuum, and it is so hot that it glows in X-rays, and at this speed it presses against the galaxy's own gas like a headwind against a sheet. The stars do not notice. Stars are compact and heavy, and they sail straight through, on the orbits they were always going to follow. The gas between the stars is different. It is diffuse, it is loosely held, and it is being stripped away layer by layer from the leading edge and drawn out behind. Look back along the direction you came from, and there is a tail, 260,000 light-years long, longer than the galaxy itself by a wide margin, made of the material the galaxy is losing. And inside that tail, in the wake, the stripped gas is compressing as it goes and lighting up. Dozens of new star clusters are forming out there, behind the galaxy, in the trail of its own dismantling. They are not bound to it. They never will be. They are being born already separated from the thing that made them, and they will be left behind in the cluster when the galaxy has passed. The process is called ram pressure stripping, and it is one of the main ways spiral galaxies are converted into the gas-poor ellipticals that fill cluster centers. Take away a galaxy's gas, and you take away its ability to make new stars. The ones it already has will live out their lives, and the galaxy will slowly redden and stop. It is also the reason cluster centers look the way they do. Go to the middle of a rich cluster, and you find giant elliptical galaxies, red, smooth, and largely finished with star formation. Go to the outskirts and you find spirals still forming stars. That gradient is not a coincidence of where galaxies were born. It is the record of what the cluster does to whatever falls into it, and ESO 137-001 is a snapshot of the conversion happening in real time. The final layer of this arrived in 2014. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomered mapped the velocity flows of about 8,000 galaxies and used those flows to define a supercluster in a new way. Instead of drawing a boundary around a region where galaxies look concentrated, they drew it the way a hydrologist defines a watershed, by which way things run downhill. Every galaxy whose motion converges toward the same basin belongs to the same structure. The result was named Laniakea, from Hawaiian words meaning immense heaven. It is 520 million light-years across, contains something like 100,000 galaxies, and the Great Attractor is the bottom of its basin. Our galaxy sits well out on an outer slope, not near the middle. The naming of Laniakea was a deliberate choice, and a good one. The word was suggested by a Hawaiian language expert at the University of Hawaii, and it acknowledges the Polynesian navigators who crossed the largest ocean on Earth using the stars, which is a more appropriate reference for a structure defined by flow than another Latin abbreviation would have been. It is also, unusually for astronomy, a name that describes the thing rather than cataloguing it. And then the map showed one more thing. The flow does not stop at the Great Attractor. It continues past it, toward the Shapley supercluster, 650 million light-years away, which contains more than 8,000 galaxies and is the densest concentration of matter in the nearby universe. Harlow Shapley catalogued it in the 1930s as an oddly rich patch of galaxies, decades before anyone understood what it might be doing to us. So the honest current account is layered. Part of our motion comes from the Great Attractor. A share, possibly a large one, comes from Shapley beyond it. And part of it, as we saw in Cetus, comes from being pushed by an emptiness on the opposite side of the sky. How the budget divides is still argued over, and how much mass remains hidden in the zone of avoidance is still not known. We know we are falling. We are still working out exactly what we are falling toward. Every person who has ever lived has been moving at 600 kilometers a second towards something none of them could see, in the direction of a constellation named after a carpenter's tool. The next entry is a constellation the sun passes through every single year, which the calendar refuses to acknowledge, and it holds the largest explosion anyone has ever measured. Number 3. Ophiuchus, the 13th sign, and the largest explosion ever measured. Ophiuchus is the serpent bearer, the man standing between the two halves of the snake we visited earlier. It is one of Ptolemy's original 48, covering 948 square degrees, 11th largest in the sky. The figure represents Asclepius, the physician of Greek myth, who learned medicine well enough to begin returning the dead to life, and was struck down by Zeus for disturbing the arrangement between the living and the underworld. The staff he carried, with a single serpent wound around it, is still the emblem painted on ambulances and stitched onto the uniforms of medical services across most of the world. Its most repeated fact is also its strangest piece of administration. The sun passes through Ophiuchus every year. It enters around the 29th of November and leaves around the 17th of December, which is roughly 18 or 19 days. That is more than twice as long as the Sun spends inside the official borders of Scorpius, which is about 7 days. By any observational definition, Ophiuchus is a constellation of the ecliptic. It is not a sign of the zodiac. The reason is that two systems were built at different times for different purposes and were never reconciled. The Babylonians, working around 2,500 years ago, divided the Sun's annual path into 12 equal segments of 30 degrees each, because 12 segments of equal size make the arithmetic of a calendar tractable. Those segments were named after the constellations that happened to sit near them at the time. The constellations themselves were never equal in size and never lined up neatly with the segments. Then, in 1930, Delport drew the modern boundaries to fit the stars, not the calendar, and the mismatch became formal. There is a further wrinkle that most people never hear. The 12 signs are not the only scheme that has ever been used, and the constellations are not the only way to divide the ecliptic. Indian astronomy uses 27 lunar mansions rather than 12 solar segments. Chinese astronomy divides the sky along entirely different lines and has done for millennia. The idea that the sky comes pre-divided into 12 is a specific inheritance from one tradition in one part of the world, and it has been treated as a property of the sky itself ever since. On top of that, the Earth's axis wobbles slowly, completing a circuit in about 26,000 years, which shifts the Sun's apparent position against the stars by roughly one full constellation every 2,000 years. The signs have drifted away from the constellations they were named after. So there are two entirely separate reasons why the sky and the calendar disagree, and the constellation that falls into the gap between them is the one holding the serpent. What Ophiuchus hides begins with the last time anybody on Earth watched a star explode in our own galaxy. On the 9th of October, 1604, a new star appeared here. Johannes Kepler began observing it on the 17th and followed it for a year, publishing a book about it under the title De Stella Nova, on the new star. At its peak, it reached about magnitude -2.5, which made it brighter than Jupiter and one of the brightest objects in the night sky. It was visible in daylight for roughly 3 weeks. It remained visible to the unaided eye for about 18 months before fading out. Supernovae of this type are not the collapse of a massive star. Kepler's star is generally classified as the thermonuclear kind, in which a white dwarf in a binary system accumulates material from a companion until it crosses a mass threshold and detonates entirely, leaving nothing behind. That distinction matters because those explosions reach a consistent peak brightness, which is what makes them usable as distance markers. The measurement of the accelerating expansion of the universe and the whole idea of dark energy rests on observations of the same kind of explosion in galaxies far outside our own. It has never been repeated. 422 years have now passed, and no supernova in the Milky Way has been seen with the naked eye since. That is a longer gap than the historical record contains anywhere else. Before Kepler's star, there was Tycho's in 1572, and before that, a scattering of events recorded by Chinese, Japanese, Arab, and European observers across the previous millennium. The timing is the part worth sitting with. Kepler's star appeared in 1604. Galileo turned a telescope on the sky in 1609, 5 years later. Humanity has had telescopes for 4 centuries, has built instruments of extraordinary sensitivity, has put observatories in orbit, and has never once caught a supernova in its own galaxy with any of them. It is not because they stopped happening. On statistical grounds, the Milky Way should produce 2 or 3 supernovae per century. Several have almost certainly gone off since 1604. They were hidden by the same dust that hides the galactic center, going off unseen behind the plane of the disk, and the only evidence we have of them is the remnants found later in radio and X-rays after the fact. A supernova at that distance today would be the astronomical event of the century by a wide margin. It would be visible in daylight, it would be studied by every instrument in orbit and on the ground, and it would produce a burst of neutrinos detectable hours before the light arrived, because neutrinos leave a collapsing core immediately while light has to fight its way out through the star. Detectors around the world are networked specifically to catch that neutrino burst and alert observatories in time to watch the star before it brightens. The network has been waiting since the 1980s. It is worth pausing on how strange that silence is, given how much else we can see. In the same 4 centuries, astronomers have observed thousands of supernovae in other galaxies, some of them billions of light-years away. We can watch a star die in a galaxy so distant that its light left before the Earth existed, and we cannot watch one die in our own. The reason is entirely geometric. Other galaxies are seen face-on or at an angle, from outside, with nothing between us and them. Our own galaxy is seen from the inside, edge-on, through the full thickness of its dust. We have the best possible view of everywhere, except here. Kepler used his own observations of the 1604 star as an argument. If the heavens beyond the moon were unchanging and perfect, as the inherited doctrine held, then a new star should not be able to appear in them at all. He measured its position carefully, showed it had no parallax and therefore lay far beyond the moon, and used it against the old cosmology directly. The remnant is still there, about 20,000 light-years away, now a shell roughly 14 light-years across, still expanding at something like 2,000 kilometers per second. The remnants that have been found tell the story clearly. Cassiopeia A is the wreckage of a star that exploded around the year 1680, close enough and bright enough in radio that it is one of the strongest radio sources in the sky, and there is no reliable contemporary record of anyone seeing it. A single ambiguous observation by John Flamsteed may or may not have caught it. Whatever happened, it happened behind enough dust that Europe, in the middle of a golden age of astronomical record-keeping, essentially missed it. Since then, there have been others found only as expanding shells, dated backward from their size and speed, with nobody's diary to match them to. 6 light-years from here, in the same constellation, sits one of the most watched stars in the sky. Barnard's star was identified by Edward Emerson Barnard at Yerkes Observatory in 1916, and it holds a record it is unlikely to lose. It has the highest proper motion of any known star, 10.3 arcseconds per year. Proper motion is the rate at which a star shifts against the background of more distant stars, and 10.3 arcseconds per year means Barnard's star crosses the apparent width of the full moon in about 180 years. Photograph it now, and photograph it in a decade, and the difference is obvious without measurement. Proper motion is also the reason Barnard's star was found at all. Barnard was working through photographic plates, comparing images of the same field taken at different times, looking for anything that had moved. That technique, blinking 2 plates against each other, was the standard method for finding nearby objects for most of the 20th century, and it is how Pluto was found as well. Nearby stars move faster across the sky than distant ones, for the same reason that a nearby tree passes a train window faster than a distant hill. Fast motion is a signature of proximity, and Barnard's star has the fastest motion of any star known. It is a red dwarf, about 1/6 the mass of the Sun, and roughly twice the Sun's age at something like 10 billion years. It is the closest single star to us, and the 4th closest star system after the 3 components of Alpha Centauri. It is also approaching, and it will pass within about 3 3/4 light-years around the year 11,800. which will make it the closest star to the Sun for a while. Barnard's star has been a fixture in the interstellar travel literature for the same reason. In the 1970s, the British Interplanetary Society ran a 5-year design study called Project Daedalus for an unmanned probe that could reach another star within a human lifetime, and this is the star they aimed it at. The design was enormous, fusion-driven, and entirely serious as an engineering exercise, and one of the reasons for the choice was the belief at the time that the star had planets worth visiting. That belief came from Van der Kamp's plates. Its history with planets is a cautionary tale that the field has never quite let go of. From the 1960s onward, Peter van der Kamp reported that decades of photographic plates showed the star wobbling, and he interpreted the wobble as the gravitational tug of one or more large planets. The claim stood for years and appeared in textbooks. It was eventually shown that the wobble correlated with maintenance dates on the telescope. The lens had been removed and refitted, and the apparent motion of the star had shifted at exactly those moments. There was no planet. There was an instrument. A candidate super-Earth announced in 2018 was later withdrawn as well, after further data showed the signal was an artifact of the star's own magnetic activity cycle rather than an orbiting body. Then, in 2024, the espresso spectrograph on the Very Large Telescope in Chile confirmed a real one. A planet about a third the mass of Earth, on a 3-day orbit, far too close to its star to be temperate, but unambiguously there. Further candidates have been reported since. 60 years of false alarms on one star, followed by a genuine detection of something so small that none of the earlier techniques could ever have found it. And then there is the explosion. On the 27th of February 2020, a team led by Simona Giacintucci announced a result about the Ophiuchus galaxy cluster, roughly 390 million light-years away. Clusters of galaxies are filled with hot gas, as we have seen. The central galaxy of a cluster usually contains a supermassive black hole, and when that black hole is consuming material, it launches jets, and those jets push into the surrounding gas and carve out cavities. This is a well-understood process, and it has been observed in many clusters. These jets are not a minor feature of clusters. They are thought to be the main reason cluster gas has not cooled and collapsed into enormous quantities of new stars. Left alone, gas that dense and that bright in X-rays would radiate away its heat and fall inward, and the central galaxies of clusters would be forming stars at prodigious rates. They are not. Something is reheating the gas at roughly the rate it cools, and the current answer is that the central black hole acts as a thermostat. Gas falls in, the black hole responds with jets, the jets reheat the gas, the inflow slows, and the cycle repeats over hundreds of millions of years. What was unusual here was the size. The cavity in the Ophiuchus cluster is large enough to hold 15 Milky Way galaxies. The energy required to excavate a hole that size, in gas that dense, is around 5 × 10⁴ joules. That is 5 times more than the previous record holder, and hundreds of thousands of times more than the outbursts seen in typical clusters. It is the largest explosion ever detected anywhere in the universe. The scale of the energy is difficult to convey without a comparison, so here is one. A typical supernova, the death of a single massive star, releases on the order of 10 to the 44th joules of light. This eruption released something like 10 orders of magnitude more than that. It would take on the order of 10 billion supernovae to do the same work, and the black hole responsible did it by feeding, not by dying. The way it was found is the part worth keeping. The curved edge in the cluster's X-ray gas had been noticed in 2016 and had been considered as a possible cavity. It was set aside because an explosion of the size that would be required did not seem possible. The feature was real, and the interpretation was rejected on the grounds of implausibility, which is a reasonable thing to do, and was, in this case, wrong. Confirming it took 4 instruments working together. The Chandra X-ray Observatory and the European XMM Newton provided the X-ray view of the hot gas. The Murchison Wide Field Array in Western Australia and the giant Metrowave radio telescope in India provided the radio view of the material the jets had deposited. When the radio emission was overlaid on the X-ray cavity, it filled it exactly. One of the astronomers involved described the fit as a hand in a glove, and that was the clinching evidence. The cavity is not a coincidence of the gas, it is a hole that something blew. The word explosion needs a caveat, because the timescale is nothing like the word implies. The eruption is thought to have unfolded over a few 100 million years. It was not a flash. It was a sustained push, running for longer than complex life has existed on Earth, and it moved enough gas to leave a permanent scar in a structure that contains thousands of galaxies. 2 more things sit in this constellation, and both are close to home. The Rho Ophiuchi cloud complex, about 460 light-years away, is the nearest star-forming region to the Sun. It contains hundreds of protostars less than 1 million years old, many still wrapped in the disks of gas and dust from which their planets are forming. When the James Webb Space Telescope released an image to mark its first year of science operations in July of 2023, this is what it chose. Not a distant galaxy. The nearest place where stars are currently being made, and Barnard 68 is a Bock globule, about 500 light-years away and roughly half a light-year across, containing something like twice the mass of the Sun in cold gas and dust at a temperature near -250 degrees Celsius. It is so dense and so opaque that not a single background star can be seen through it. In a visible light image, it appears as a hole in the sky, a patch where the stars simply stop, and for a long time, that is what such objects were assumed to be. They are not holes. They are the darkest objects in the sky, and this one is expected to collapse under its own weight and ignite as a star within a few 100,000 years. Ophiuchus also holds more Messier globular clusters than almost any other region of the sky. 7 of them, because this direction looks toward the galactic bulge, where globular clusters concentrate. The globular clusters are worth a closing word because they are the oldest structures in the galaxy. Each one is a sphere of hundreds of thousands of stars, most of them 12 or 13 billion years old, formed before the Milky Way's disk had assembled and orbiting the galaxy on long, steeply inclined paths ever since. They concentrate toward the galactic center, which is why so many of them appear in this direction. Their distribution was what Harlow Shapley used in 1918 to work out that the Sun is not at the center of the galaxy at all, but well out toward the edge of the disk. He determined the shape and scale of our galaxy by counting where the old clusters were, and a great many of them were in Ophiuchus. The last time a human being watched a star explode in this galaxy without a telescope, Shakespeare was still writing, and the fact that nobody has seen one since is not evidence that the galaxy has gone quiet. It is a measure of how much of it is hidden from us. And the second entry on this list contains a star that a deaf teenager solved with nothing but his eyes, and a sound that has been playing continuously for 2.5 billion years. Number 2, Perseus, the demon star and the deepest note in the universe. Perseus is one of Ptolemy's original 48, 615 square degrees, 24th by area, sitting in the northern winter Milky Way between Andromeda and the Charioteer. Most people know it for one night a year. The Perseid meteor shower radiates from this constellation every August, when the Earth passes through the debris trail of comet Swift-Tuttle, a body with a nucleus about 26 kilometers across that last came through the inner solar system in 1992. The meteors are grains of that comet, most of them smaller than a grain of sand, entering the atmosphere at around 60 kilometers per second and burning up 70 or 80 kilometers above the ground. It is the most reliably watched meteor shower in the Northern Hemisphere, and it has been recorded for nearly 2,000 years. Perseus also gave its name to the spiral arm one step outward from our own. We live in a minor arm, sometimes called the Orion Spur. The next major arm out, away from the galactic center, is the Perseus arm, and a great deal of what we see in this direction sits in it. The Perseus arm is a useful thing to be able to point at, because it makes the structure of the galaxy concrete. Spiral arms are not solid objects that stars are attached to. They are density waves, regions where matter piles up temporarily as it orbits, in the same way traffic bunches on a motorway without any individual car staying in the bunch. Stars pass into an arm, are compressed along with the gas, and pass out the other side. The arm persists, the contents change. When you look toward Perseus on a winter evening, you are looking outward through our own minor arm and across the gap to the next major one, and most of the bright clusters in that direction are objects the density wave has recently made. In the classical figure, Perseus is holding the severed head of Medusa. The star marking that head is Beta Persei, and its Arabic name is Ras al Ghul, the head of the demon, from which we get the name Algol. Every 2.87 days, Algol drops from magnitude 2.1 to magnitude 3.4, stays dim for about 10 hours, and then recovers. That change is large. It is not subtle, it is not a matter for instruments, and it is entirely visible to the unaided eye if you know which star to watch and you look on the right night. A star that is clearly one of the brighter stars in the region becomes clearly one of the fainter ones, and then comes back on a schedule you could set a calendar by. Cultures across the ancient world associated this star with misfortune. It appears as a demon, an ogre, a ghoul, or a severed head in Greek, Arabic, Hebrew, and Chinese traditions, and the name has stayed demonic through every language it has passed through. Whether any of those cultures knew it varied is a separate question we will come back to. It is worth asking why nobody worked it out sooner, because the answer is not that the change is hard to see. Algol had been in the sky, doing this, for the entire history of civilization. The eclipse is deep enough to notice. The period is short enough that anyone paying attention for a fortnight would catch several, and the star is bright and easy to find. What was missing was not capability. It was the expectation that a star might change at all. In a cosmology where the heavens are perfect and fixed, a star that dims is a mistake in the observation, and mistakes get discarded. The observation required a mind willing to record something the framework said should not happen. The explanation came from a teenager. John Goodricke lost his hearing to a severe illness in early childhood and was educated at a school for the deaf in Edinburgh, then at a Warrington academy that was unusual for taking students the universities would not. He could not hear and he did not speak easily, and in the 18th century that closed most doors. It did not close observation. In 1783, at the age of 18, he made a systematic series of naked-eye brightness estimates of Algol, night after night, comparing it against neighboring stars whose brightness did not change. From those estimates, he established the period to within a few minutes of the value we use today. Then he did the harder thing, which was to propose a mechanism. His suggestion was that a large dark body was passing periodically in front of the star and blocking part of its light. He was right. Algol is an eclipsing binary. Two stars orbit one another in a plane that happens to be oriented nearly edge-on from our position, so that once each orbit, the dimmer star passes across the face of the brighter one. There is a third star in the system as well, orbiting further out. The whole arrangement sits about 90 light-years away. That proposal, from an 18-year-old with no instrument beyond his eyes and a notebook, was the origin of the study of variable stars as a field. He also determined the period of Beta Lyrae and studied Delta Cephei, and Delta Cephei turned out to be the prototype of the class of variable stars whose brightness cycles reveal their true luminosity, which became the measuring stick astronomers used to establish the scale of the universe a century and a half later. Goodricke did not work alone, and it is worth naming his collaborator. Edward Pigott was a considerably older and more experienced astronomer who lived nearby in York and had an observatory, and the two of them worked as a partnership, dividing stars between them and comparing results. Pigott suggested targets, provided instruments, and continued the work for decades after Goodricke was gone. Between them, in a few years, they found the first handful of variable stars ever identified as such, and effectively founded the field. Pigott outlived his young colleague by more than 40 years. He was awarded the Copley Medal, the most senior award of the Royal Society, at 19. He died at 21 of pneumonia, which he is generally thought to have contracted while observing. 3 years of work. That is the whole career. And the star, he explained, is doing exactly what he said it was doing, on exactly the schedule he measured, tonight, and it will do it again in 2.87 days. There is a claim attached to Algol that needs careful handling, because it is repeated more confidently than the evidence supports. In 2013, a group of Finnish researchers led by Lauri Jetsu analyzed the Cairo calendar, an Egyptian papyrus dating to roughly 1,200 years before the Common Era, which assigns each day of the year a rating as lucky or unlucky. They reported a statistically detectable period of 2.85 days in the pattern of those assignments, which is close to Algol's period after allowing for the slow change in that period over 3,000 years. Their argument was that the scribes were tracking the star. If that is right, Algol is the oldest recorded variable star, followed more than 3,000 years before Goodricke. The claim is contested and has not been generally accepted. Reasonable objections exist about the statistics, about whether the calendar's structure could produce such a period for unrelated reasons, and about whether the period match is as good as claimed. It is worth telling as a possibility. It is not a fact. Algol also produced a genuine crisis in stellar theory, and its resolution is now a foundation of the field. In a binary system, the more massive star should evolve faster. Mass drives the rate of fusion, and a heavier star burns through its fuel far more quickly, so the heavier of two stars born together should reach the swollen giant stage first. In Algol, that is backward. The less massive star is the evolved one. That is the Algol paradox, and it went unexplained for decades. The resolution is that the star, which is now less massive, used to be the heavier one. It evolved first, exactly as theory required, swelled up as it did so, and expanded past the point where its own gravity could hold its outer layers against the pull of its companion. Material then flowed from one star to the other, in quantity, over a long time, until the mass ratio had reversed. Mass transfer between stars is now understood to be central to an enormous range of phenomena, including novae, X-ray binaries, and one entire class of supernova. That whole framework began with a star named after a demon, behaving in a way that should not have been possible. 240 million light-years behind Algol sits the Perseus cluster. Catalogued as Abel 426, It is one of the most massive objects in the known universe and the brightest cluster in the X-ray sky. It contains thousands of galaxies embedded in gas at around 50 million degrees, and because it is bright and relatively close, it has been observed by essentially every X-ray observatory ever flown. In 2002, Andrew Fabian and colleagues obtained a very deep Chandra observation of that gas. Deep in this context means simply pointing the telescope at the same place for a very long time so that faint structure emerges from the noise. What emerged were ripples, concentric arcs in the density of the gas, spreading outward from the central galaxy for hundreds of thousands of light years. Ripples in a gas are pressure waves. Pressure waves in a gas are sound. The waves were being generated by the supermassive black hole at the cluster's center, which inflates bubbles of hot material as it launches jets, and each of those bubbles pushes on the surrounding gas as it expands. The push propagates outward. It is exactly the mechanism by which a loudspeaker cone makes a sound, operating on a cluster of galaxies. Everything about that measurement is indirect, and it is worth appreciating how it was possible. Chandra does not detect sound. It detects X-ray photons, one at a time, and records where each one arrived and how energetic it was. Over a long enough exposure, the map of where photons landed becomes a map of where the gas is denser, because denser gas emits more X-rays. The ripples are variations of a few percent in that density, spread over regions 100,000 light-years across, and they only became visible after roughly a full day of accumulated exposure time. The deepest note in the universe was found by counting individual particles of light for long enough that a pattern emerged from the noise. The team calculated the pitch. It is a B-flat, 57 octaves below middle C. A piano covers about 7 octaves. Human hearing covers about 10. 57 octaves below middle C is roughly 1,000,000 billion times lower in frequency than the deepest sound a human ear can register, and a single complete wave takes about 10 million years to pass a fixed point. It is the deepest note ever detected in the universe, and it has been sounding at approximately that pitch for 2.5 billion years. Stay in that gas for a moment. You are suspended somewhere inside a cluster of galaxies, and there is essentially nothing around you. The gas here is thinner than the best vacuum any laboratory on Earth has ever produced, and it is at 50 million degrees, which in a medium this thin means the individual particles are moving quickly, and there are almost none of them. Galaxies hang in it at enormous separations, each one 100 billion stars, and from here they are points. Then a wave arrives. There is nothing to hear and nothing to feel, because the pressure change is a fraction of a percent and it is spread across 100,000 light years. It is not a sound in any sense a body could register. It is a slow, shallow compression moving outward through the gas at the speed sound travels in a medium this hot, which is over 1,000 kilometers per second, and even at that speed, the wave takes 10 million years to go from its crest to its next crest. To be present for one full cycle of this note, you would have to sit here from the first upright ape to something 10 times further in the future than that. And it has been playing since before there were animals on Earth. There is a reason the sound matters beyond its novelty. Cluster gas that bright in X-rays should be cooling. Cooling gas should sink to the center, become dense, and form stars in enormous quantity, and the central galaxies of clusters should therefore be among the most productive star-forming regions in the universe. They are not. They are red and quiet. Something is putting heat back into the gas at approximately the rate it is being radiated away, and these sound waves are one of the main candidates for how the energy is delivered. The note is not decoration. It may be the mechanism that keeps the cluster from collapsing in on itself. The energy stored in the cavities that produced those waves is equivalent to about 100 million supernovae. In 2022, NASA released a sonification of the Perseus data, shifting the frequencies upward by 57 and 58 octaves so that human ears could hear something with the same relationships in it. It sounds like a low, drifting wail. It is not what the cluster sounds like, because the cluster does not sound like anything. It is the closest translation available. The central galaxy, NGC 1275, has its own unsolved feature. It is threaded with filaments of cool gas, some of them 20,000 light-years long, hanging in the 50 million degree medium that fills the cluster. By every ordinary calculation, those filaments should not survive. They should evaporate or disperse or be torn apart by turbulence within a small fraction of the time they have evidently existed. They have not. The current explanation is that they are held together by magnetic fields, threads of magnetism running along their length and giving them enough structural coherence to persist inside a furnace. They are among the best evidence available anywhere for organized magnetic structure on galactic scales, and they are visible in images as thin red streamers reaching out of a bright galaxy into apparently empty space. Perseus also carries an argument about dark matter that has not been settled in 12 years. In 2014, two independent teams reported an unexplained X-ray emission line at an energy of about 3.5 kilo-electron-volts in the Perseus cluster and in stacked observations of other clusters. No known atomic transition accounted for it cleanly. One proposal was that it came from the decay of a sterile neutrino, a hypothetical particle that has been a dark matter candidate for decades. If confirmed, it would have been the first non-gravitational detection of dark matter in history. In 2016, the Japanese satellite Hitomi observed Perseus with spectral resolution far beyond anything previously flown, precisely the capability needed to settle it. It did not see the line where it should have been. Hitomi returned about 5 weeks of data. Then a chain of failures in its attitude control software caused the spacecraft to spin up until it broke apart in orbit. The instrument that could have answered the question was destroyed before it had properly started. 12 years on, the 3.5 kilo-electron-volt line is neither confirmed nor dismissed. The 3.5 kilo-electron-volt story is a good illustration of how these questions actually get decided, which is rarely by a single clean result. Some later observations found the line. Others, looking at objects where it should have been strongest, did not. Analyses disagreed about the treatment of instrumental effects and about whether a mundane atomic transition in the cluster gas from an element in an unusual ionization state could account for it after all. The proposal has not been ruled out, and it has not been established. It sits in the literature as an open item, which is where a great many things sit. Nearer to home, Perseus holds the double cluster, two rich open clusters catalogued as NGC 869 and NGC 884, sitting about 7,500 light-years away in the Perseus arm. Both are around 13 million years old. Both contain hundreds of bright young stars, and they are close enough together on the sky to appear as a single soft patch to the unaided eye. Hipparchus catalogued them around 130 years before the Common Era, which makes them one of the oldest recorded deep sky objects in the world. The double cluster also carries a quieter fact. Both clusters are dominated by hot blue stars, which are the most massive kind and the shortest lived. At 13 million years old, these clusters are extremely young by any standard. The Sun is 4.5 billion years old, which is roughly 350 times longer. Everything currently making those clusters bright will be gone within a few tens of millions of years, ending as supernovae, and what remains will be a loose scattering of ordinary stars that nobody would pick out. What we are looking at when we look at them is a brief phase, caught by accident. And GK Persei flared as Nova Persei in 1901, becoming for a short time one of the brightest stars in the sky. It was a white dwarf that had accumulated enough material from a companion to trigger a runaway reaction on its surface. The shell it threw off is still expanding, and Chandra has followed it for years as a miniature supernova remnant, running on a timescale a human being can actually watch. A deaf teenager watched one star blink and worked out that stars come in pairs, and 2 centuries later, the same constellation gave us the lowest note anyone has ever measured, sounding steadily for longer than there has been complex life on Earth. Which leaves one constellation. And the reason it is first is not what is inside it. It is why so much of it ended up there. Number 1, Cygnus, the swan at the end of every unanswered question. Cygnus is the swan, flying south down the length of the Milky Way, and to most northern observers, it is simply the Northern Cross. It is one of Ptolemy's original 48, 804 square degrees, 16th by area. Unlike almost everything else on this list, it looks like the thing it is named after. A long neck, a body, 2 wings stretched wide, and a bright star at the tail. It is one of the few constellations that a person can find once and never lose. Its brightest star is Deneb, at the tail, and Deneb is one of the more remarkable objects visible to the unaided eye. It is a blue-white supergiant, radiating something like 200,000 times as much energy as the Sun. It also has a distance we still cannot pin down. Estimates range from roughly 1,500 to 3,000 light-years, and that uncertainty of nearly a factor of 2 makes it one of the least precisely measured bright stars in the sky. If it sits at the far end of that range, it is among the most luminous stars anyone has ever seen without a telescope. Deneb is one corner of the summer triangle, and the other 2 corners have distances known to within a few percent. So the reason Cygnus tops this list is not that it is oddly drawn or carelessly named. The reason is geometry, and it only becomes clear after the other 9. We live in a spiral galaxy, in a minor arm, in a disk. Look towards Sagittarius, and you look inward, through the bulge, into the maximum possible depth of dust. Look toward Coma Berenices, and you look straight out of the disk, through almost nothing, and see other galaxies. Look toward Cygnus, and you do something different from either. You look along the length of our own spiral arm. Not across it, along it. The line of sight from here toward Cygnus runs parallel to the local structure of the galaxy, which means you are looking down a corridor rather than across a room. It is the deepest sightline into our own galaxy that the unaided eye can take, and running down the middle of it, splitting the band of the Milky Way in 2, is the Great Rift, a lane of dark dust in the foreground that makes the depth behind it obvious. Stand outside on a clear night in July and look up, and you can see the geometry directly. The swan is nearly overhead. Beneath it, the Milky Way runs from horizon to horizon, and it is brighter and more textured here than anywhere else in the northern sky, because there is more of it in this direction. The dark lane down the center is not empty. It is dust a few thousand light-years away, sitting between you and everything behind it. Follow the line of the swan's body outward. The first few hundred light-years hold ordinary nearby stars. At 2,400 light-years, there is the shell of a star that exploded while people were painting on cave walls, 120 light-years across and still moving. At about 4,600 light-years, there is one of the most productive star-forming complexes in the galaxy, 1 million solar masses of gas, making new stars right now. At 7,200 light-years, there is a black hole, 21 times the mass of the Sun, pulling a stream of gas off a blue supergiant. Beyond that, the arm keeps going, and the dust closes in, and eventually the corridor fills, and the view ends. Everything in this entry is stacked along that one line, and you are looking at all of it at once, without being able to separate any of it by eye. A constellation is a direction, not a place, and this is the direction with the most behind it. Start with the oldest thing here. In 1838, Friedrich Bessel picked a dim double star in Cygnus, catalogued as 61 Cygni. He chose it deliberately, and for a good reason. It has an unusually large proper motion, which suggested it was nearby, because nearby things appear to move faster. What he was attempting had defeated everyone who had tried it for 200 years. If the Earth orbits the Sun, then a nearby star should appear to shift slightly against the more distant background as the Earth moves from one side of its orbit to the other, in the same way a finger held at arm's length shifts against the far wall when you look with one eye and then the other. That shift is called parallax, and measuring it gives the distance directly, with no assumptions. The problem was that the shift is tiny. For 61 Cygni, it amounts to about 1/3 of an arcsecond, which is roughly the angle a coin makes at a distance of 10 kilometers. Failure to detect it had been used for centuries as an argument that the Earth does not move. Bessel was not working alone, and he was not the only one close. Thomas Henderson had measured a parallax for Alpha Centauri from the Cape of Good Hope and sat on the result for years before publishing, and Friedrich Georg Wilhelm Struve was working on Vega in Russia at the same time. All three results appeared within about a year of each other, after 2 centuries in which nobody had managed it at all, because the instruments had finally become good enough. Bessel published first, and he published with the smallest uncertainties, which is why the credit generally goes to him. Bessel measured it. He got about 11 light-years, which is close to the modern value. It was the first time any human being had measured the distance to a star. Everything we know about the scale of the universe outside the solar system rests on a chain of measurements, and the first link in that chain was fixed in this constellation. Now the black hole. In 1964, a sounding rocket carrying Geiger counters above the atmosphere for a few minutes found a powerful source of X-rays in Cygnus. It was catalogued as Cygnus X1, meaning the first X-ray source found in Cygnus. At that point, nobody knew what it was, because X-ray astronomy was a few years old and consisted mostly of brief rocket flights. In 1971, better radio positions allowed it to be tied to a specific star, a blue supergiant catalogued as HDE 226868, roughly 40 times the mass of the Sun. That star was orbiting something every 5.5 days. The something was invisible, and from the orbit it was clearly too massive to be a neutron star, which has a hard upper mass limit set by the physics of the material it is made of. What makes the X-rays is worth describing, because a black hole itself emits nothing. Material pulled off the companion star does not fall straight in. It has angular momentum, so it spirals, forming a flattened disk that orbits faster and faster as it approaches. Friction between adjacent layers of that disk, moving at different speeds, heats the gas enormously. By the time material reaches the inner edge, it is at millions of degrees, and gas at millions of degrees radiates in X-rays. Everything we see from Cygnus X1 is the light of matter being heated on its way down. The object itself is a region where the light stops. Cygnus X1 became the first object that most astronomers were prepared to call a black hole. In 1974, Stephen Hawking bet Kip Thorne that it was not one. He explained the logic himself, and it is a fair piece of reasoning. He had spent his career working on black holes. If they turned out not to exist, that career would have been spent on nothing, and the bet was insurance. He would at least win something. The stake was a one-year subscription to the magazine Private Eye for Hawking if he won, against a subscription to Penthouse for Thorne if he lost. The evidence accumulated for 16 years. In June of 1990, while visiting Caltech, Hawking went into Thorne's office with an entourage of family, nurses and friends, found the framed wager on the wall, wrote a concession on it and validated it with his thumbprint. The story has an ending nobody expected. In 2021, radio astrometry using the Very Long Baseline Array compared precise positions measured in 2011 and in 2020 and produced the best distance yet, 7,200 light-years, about 20% further away than everyone had assumed. Distance matters, because everything else scales with it. The revised mass came out at 21 solar masses. That made it the heaviest stellar mass black hole ever weighed without gravitational waves, and it created a genuine problem. Massive stars shed enormous quantities of material in their winds over their lifetimes. The models said a star in this galaxy, with this composition, could not hold on to enough mass to leave a 21 solar mass remnant. The measurement forced a revision of how strong those winds actually are. It also spins at more than 95% of the maximum rate general relativity permits, which is another thing that is hard to arrange. Then there is the star nobody can explain. In 2015, volunteers working through Kepler light curves flagged an object catalogued as KIC 8462852. They were part of Planet Hunters, a project that put the data in front of ordinary people on the internet because human pattern recognition is better than software at spotting things software was not written to look for. That is exactly what happened. The automated planet-finding algorithms had discarded this star's dips as noise because they did not match the shape a transiting planet makes. The volunteers looked at the curve and saw that something was clearly there. Tabetha Boyajian led the paper describing it. The title was a question: where's the flux? A gas giant crossing the face of a sun-like star blocks about 1% of its light for a few hours on a strict repeating schedule, and the dip has a clean, flat-bottomed shape. This star was dropping by up to about 22%. The dips came on no schedule at all. Some lasted days, some lasted weeks. Their shapes were jagged and asymmetric, unlike anything a spherical object crossing a disk could produce. Jason Wright published a paper, written in deliberately careful language, noting that the light curve was consistent with what a partially completed structure built around a star might look like. That is not a claim that it was one. It is a statement about what the data did not exclude, which is a different and more honest thing, and it was widely reported as the former. Radio and optical searches for artificial signals from the star found nothing. In 2017, a crowdfunding campaign backed by more than 1,700 people paid for a dedicated observing campaign to catch a dip as it happened, with multiple telescopes watching in multiple colors at once. That is what was needed, and nobody was going to allocate major observatory time to it on speculation. It worked, and the answer came in 2018. The dips are color-dependent. They are noticeably deeper in blue light than in red, by a factor of roughly 1.5 to 2. That single fact settles a great deal. A solid object blocks every color equally. A wall is a wall, regardless of wavelength. Fine dust does not. Dust scatters short wavelengths preferentially, which is why sunsets are red and why the daytime sky is blue. Material that dims blue light more than red is dust, with particle sizes on the order of a fraction of a micron. So it is not a structure, it is dust. That closed the megastructure question. It did not close the star. Why an otherwise ordinary F-type star should be surrounded by irregular, dense, aperiodic clouds of fine dust, in quantities large enough to block a fifth of its light, and why it also appears to show a slow, long-term fade in archival photographic plates going back a century, are questions that remain open. Proposals include the debris of a shredded planet or moon, an unusually large family of disintegrating comets, or something internal to the star that we have not identified. And then there is the field itself. From March of 2009 to May of 2013, the Kepler Space Telescope stared without moving at a single patch of sky about 115 square degrees across, centered on Cygnus and its neighbor Lyra. It measured the brightness of roughly 150,000 stars every 30 minutes, continuously for 4 years. The field was chosen partly because from Kepler's orbit, the Sun never gets in the way of it. The method Kepler used is worth stating plainly because it is almost absurdly simple. If a planet crosses the face of its star as seen from here, the star gets slightly dimmer for a few hours. Measure the brightness precisely enough for long enough, and you can detect the dip. The catch is precision. A planet the size of the Earth crossing a star like the Sun blocks about 1 part in 10,000 of its light, which is like noticing a single moth crossing a stadium floodlight from several kilometers away. Kepler was built to do exactly that for 150,000 stars at once, which is why it could not move and why it stared at one field for 4 years. There is a geometric limit built into the technique. A transit only happens if the planet's orbit is nearly edge-on from our position, and for most planetary systems it is not. But the great web of galaxies is always in motion. So the 2,600 that Kepler found are not the planets in that patch of sky. They are the small fraction whose orbits happen to line up, which is how a survey of one patch became a statement about the whole galaxy. You count what you can see, divide by the probability of being able to see it, and the answer comes out enormous. It found more than 2,600 confirmed planets. Almost everything we know statistically about how common planets are came out of that one patch of sky. That most stars have them. That small planets are more common than large ones. That planets in the temperate zone of their star are not rare. That there are, in this galaxy, more planets than stars. Every one of those statements is a conclusion drawn from staring at Cygnus for 4 years and counting how often the light flickered. 2 more. Cygnus A sits about 760 million light-years away. Grote-Reber detected it as a radio source in 1939, working alone with a 9-meter dish he had built in the back garden of his house in Wheaton, Illinois, at a time when he was effectively the only radio astronomer on Earth. Professional astronomy had no interest in radio, and a man with a day job built the instrument himself and made the first radio map of the sky. In 1954, Walter Baade and Rudolf Minkowski identified the source optically as a galaxy. It was the first radio galaxy ever recognized, and that single identification proved that radio sources could be extragalactic, which opened the entire universe to radio astronomy. Its twin jets extend about 300,000 light-years, powered by a central black hole of perhaps 2.5 billion solar masses, and the hotspots where those jets terminate are among the brightest radio sources in the sky, despite the distance. The constellation also holds the North American Nebula, a large region of glowing hydrogen, whose shape, entirely by accident of where the foreground dust happens to sit, reproduces the outline of a continent, including a recognizable Gulf of Mexico. It is about 20 times the area of the full moon on the sky. Next to it is Cygnus X itself, one of the most active star-forming complexes in the galaxy, roughly 1 million solar masses of gas at about 4,600 light-years, containing some of the most massive young stars known within reach of detailed study. And the Veil Nebula, the visible portion of the Cygnus Loop, is the wreckage of a star that exploded somewhere between 10 and 20,000 years ago, about 2,400 light-years away. The shell is now around 120 light-years across and spans about 3 degrees on the sky, roughly 6 times the width of the full moon. Its filaments are shock fronts, still moving outward at hundreds of kilometers per second, glowing where they slam into interstellar gas. The light of that explosion arrived here while people were painting animals on cave walls, and nothing in the historical record mentions it, because there was no historical record. So here is the accumulation, laid out. The first measured distance to a star. The first object accepted as a black hole. The first radio galaxy ever identified. The field that produced most of what we know about how common planets are. The heaviest stellar mass black hole weighed by conventional means. And the single most inexplicable star in the catalogue. All of it in one bird-shaped patch of sky. And the reason is not that Cygnus is favored. It is that Cygnus is the direction in which we can see furthest into our own galaxy. More stars in the field means more rare objects in the field. A deeper corridor means more chances for something along it to be strange. Kepler pointed there for precisely that reason, and Kepler is why Boyajian's star was found, and Boyajian's star was found by volunteers rather than by software because somebody had to be looking. Which is the thread that has been running under all 10 entries tonight. Bell found the first pulsar because she read the chart paper. Fabricius found the first variable star because he needed a reference point and noticed it had moved. Goodricke measured Algol because he watched it for months. Zwicky found dark matter because he did the arithmetic and did not discard the answer. Eamon found the wow signal several days after it had already happened, on a printout nobody else had opened. The Great Attractor was found by people measuring the same galaxies twice, 2 different ways, and taking the disagreement seriously. The strangeness on this list did not come from the sky being arranged strangely. The 88 squares are a filing system we invented, drawn by a committee in 1930 along lines that no longer even match the coordinate grid. What any one of them contains is not a property of the square. It is a property of how long we have looked through it, and how carefully, and whether somebody bothered to check the part that did not fit. Every one of those 88 squares is a window rather than a wall. Behind the faintest of them there was a galaxy. Behind the smallest of them there was the thing that moves us. And behind the one that looks most like what it is named after, there was the deepest view we have of the place we live. Sleep well, and good night.